Welcome. Tonight, we invite you to settle into the quiet dark, to pause, and to question the ground beneath your feet. We are going to question the gentle warmth of the daylight air, the apparent stability of the distant horizon, and the very nature of the color blue. Most of us spend our entire lives clinging to a comforting, silent assumption. We assume that Earth is fundamentally a world of sunlight, open skies, and familiar landscapes. We gaze at photographs taken from space, that iconic blue marble floating serenely in the vast void of cosmic blackness, and we feel an immediate, deeply rooted sense of warmth and familiarity. We see swirling white clouds drifting lazily over a vibrant, inviting ocean, and our minds automatically whisper that this is home. We imagine the sea as a clear, sunlit paradise where life unfolds in plain view under golden rays. That beautiful, reassuring image of the blue marble is a profound lie. The sunlit world we know is not the rule of planet Earth. It is a razor-thin, fleeting, and extremely fragile exception. That glorious blue color defining our planet from space is nothing more than a trick of light and physics, a temporary optical illusion caused by photons interacting with water molecules. It is merely a microscopic layer of paint on a dark, massive skyscraper that has no interior lights turned on. Peel back that uppermost skin, just a tiny fraction of the ocean's total depth, and the blue vanishes instantly. The true baseline reality of planet Earth is not color or light. It is total, suffocating, crushing, eternal blackness that has persisted undisturbed for billions of years. Over 95% of the living space on this planet exists in a permanent midnight where the sun is nothing more than a distant, forgotten myth. Why does the ocean deceive us so completely? The answer lies in the uncompromising physics of light itself. Imagine standing on the deck of a vessel in the middle of the open Pacific Ocean. The midday sun shines brightly overhead. The surface water looks clear, almost like liquid glass. However, water is not glass. It is a relentless thief. When a beam of sunlight strikes the ocean's surface, it arrives carrying the full spectrum of visible light: red, orange, yellow, green, blue, indigo, and violet. The moment those energetic photons penetrate the liquid, a violent process of atmospheric absorption begins. Water molecules aggressively absorb light energy, starting strictly with the lowest energy, longest wavelengths. The very first victim of this aquatic theft is the color red. Red light possesses low energy and struggles to push through the physical density of liquid water. Within the upper 5 meters, barely the length of a single family car, the color red is physically erased, absorbed by liquid water molecules, and transformed into thermal energy. If a diver cuts their hand at a depth of 10 to 15 meters, the blood escaping the wound does not appear red. It appears as a dark, murky green or pitch black, simply because there are 0 red light photons left in the surrounding water column to reflect back into the human eye. Descending deeper, past 20 meters, orange wavelengths are stripped away, followed rapidly by yellow and green. The water acts as an unyielding filter, progressively stripping warmth from the spectrum. By the time you reach 40 meters, blue light is the sole survivor. Blue light has short, high-energy wavelengths that dodge water molecules far more effectively, scattering in all directions and bouncing back upward toward the surface. That is the single reason the ocean appears blue to our eyes. You are looking at the surviving remnants of a light spectrum that has been eaten by the sea. Even blue light cannot survive forever. As we sink deeper toward 150 meters, the brilliant blue fades into a heavy, melancholic indigo twilight. The blazing disk of the sun diffuses into a faint, sickly glow. We experience Snell's window, an optical phenomenon where the entire bright sky above is compressed into a shrinking, dim circle of light directly overhead. Here, at the boundary of the photic zone, human familiarities end. Almost all human activity, scuba divers, military submarines, and marine industries operate exclusively within this thin, sunlit skin. We map shallow coral reefs, track commercial fish, and mistakenly believe we understand the ocean. We are like astronauts who stepped onto the moon, kicked a handful of dust, and declared they had explored the entire universe. Beneath us, the temperature plummets, the hydrostatic pressure mounts, and the blue fades into grey, preparing us for the true, living mysteries of the twilight realm. As we linger in this rapidly darkening threshold, it becomes impossible to ignore how completely our human senses fail us. On land, sight is our primary sensory shield. We rely on the vast reach of visible light to warn us of danger from hundreds of meters away, to locate food, to navigate terrain, and to identify companions. Sunlight gives us context, order, and a sense of mastery over our environment. But as you descend through this relentless column of water, every familiar sensory rule is systematically dismantled. The light does not simply dim, the very structure of visual space collapses. Consider what happens to your perception of distance and scale. In the upper 50 meters, as the red and orange wavelengths are stripped out, contrast begins to soften. Shadows lose their sharp edges and dissolve into a uniform, ambient haze. Objects do not cast distinct shadows behind them. Instead, they simply fade into the monochromatic blue envelope. By 70 meters, your depth perception becomes profoundly compromised. A massive, looming wall of rock and a tiny floating particle of debris can look strangely identical in scale because there are no warm highlights or cast shadows to give the human brain visual cues about texture or relief. Everything is reduced to a soft, phantom silhouette hovering in a boundless blue void. This loss of visual anchors triggers a subtle but undeniable physiological response in human visitors. Without a solid floor beneath your feet or a distinct horizon line ahead, the inner ear and the visual cortex begin to disagree. On land, your brain constantly cross-references the horizon with gravity to keep you balanced. Here, suspended in three-dimensional liquid darkness, up and down lose their absolute meaning. If you close your eyes for just 10 seconds, you can easily rotate upside down without realizing it until you open them and look at the rising trail of your own exhaled air bubbles. The sea strips away your spatial orientation, forcing you to realize that human consciousness was designed entirely for a two-dimensional terrestrial surface illuminated by a warm yellow star. Furthermore, the physical behavior of water creates an eerie optical phenomenon known as forward scattering. When photons of remaining blue-green light travel through the water column, they do not just pass straight through. They collide with suspended microscopic organic matter, tiny mineral grains, and living planktonic cells. Each collision bounces the photon off at a slight angle. This means that even the faint light that manages to penetrate to a depth of 100 meters is no longer traveling in straight, direct lines from the sun. It has been bounced, scattered, and diffused so many times that it arrives from all directions at once. The light becomes directionless. You can no longer look up and pinpoint the position of the sun. You are simply encased inside a glowing, dim, indigo sphere that grows darker with every single meter you descend. It is at this critical threshold, between 100 and 200 meters down, that the ocean transitions from a world defined by solar energy to a world defined by biological necessity. Above this line, primary production thrives. Microscopic phytoplankton absorbs solar photons, converting carbon dioxide and dissolved nutrients into organic sugars through photosynthesis. This single biochemical process forms the foundational base for virtually all familiar marine food webs. Millions of tons of plant life convert light into fuel, supporting vast schools of fish, roaming pods of whales, and intricate coral reef communities. However, as light intensity drops below 1% of surface levels, a hard biological wall is reached. Photosynthesis becomes mathematically impossible. Plants cannot harvest enough photons to produce more energy than they expend simply maintaining their cellular structures. At this precise optical boundary, the living ocean undergoes a profound structural shift. The world of autotrophs, organisms that make their own food from sunlight, comes to a complete and permanent end. Below this depth, every single living creature must become a consumer, a scavenger, or a predator. Imagine an entire world that receives no direct energy input from the sky, a realm where no plant has ever grown, no leaf has ever unfolded, and no flower has ever bloomed. Everything that lives below this line is fundamentally dependent on the crumbs falling from the sunlit table far above. Life here is forced to exist on the scraps, the waste, and the drifting remains of a surface world it will never see. This creates a relentless, unforgiving economic reality where every calorie is guarded with extreme evolutionary desperation. To survive in this light-starved economy, deep water organisms cannot afford the extravagant, energetic budgets of surface animals. A fast-swimming dolphin or a high-speed tuna expends colossal amounts of energy maintaining warm body temperatures, powering massive muscle structures, and constantly searching for prey. They can afford this lifestyle because the sunlit surface layer is bursting with abundant, photon-fueled food sources. But in the dim twilight zone, such a strategy would lead to swift and absolute starvation within days. Instead, the creatures that inhabit this transitional layer are masters of extreme metabolic conservation. Their bodies are built from lightweight, water-dense tissues rather than heavy, dense muscle mass. Their bones are soft, flexible, and minimal, reducing the metabolic cost of building and maintaining a heavy skeleton. Many species possess cold, slow-burning metabolisms that operate at a fraction of the speed seen in surface animals. They do not waste precious energy swimming continuously through the water column. Instead, they hover, drift, and wait with infinite patience for the rare chance encounter with something edible. This spatial transition also changes the very nature of biological encounters. In the sunlit world, hunting is largely a visual game played across wide-open distances. A hawk spots a mouse from hundreds of feet in the air. A marlin locks eyes with a school of sardines from tens of meters away. But as light vanishes into the indigo gloom, the visual radius contracts dramatically. At 150 meters, an animal's effective visual field is reduced from hundreds of meters to a few short feet. Beyond that distance, everything dissolves into the uniform gray background. This shrinkage of the visual field alters predator-prey dynamics in dramatic ways. Stealth becomes far more valuable than raw speed. An animal does not need to outrun its enemy across miles of open ocean. It only needs to remain undetected across a distance of 2 or 3 meters. The entire aquatic environment turns into a perpetual game of hide-and-seek played out in slow motion. Creatures adapt by developing incredibly sensitive lateral line systems arrayed along their flanks, capable of detecting the microscopic pressure waves generated by the twitch of a single fin nearby. Others develop hyperextended sensory barbels and delicate whiskers that reach out into the dark like biological tripwires. As we linger here at the bottom of the photic layer, looking down into the vast, ink-black abyss that plunges thousands of meters further into the earth, a sense of profound humility begins to settle over the mind. Human civilization has built sprawling cities, launched satellites beyond the solar system, and mapped the surfaces of distant planets. Yet, we live on a planet where the vast majority of the physical space is entirely alien to our natural biology. We are surface dwellers, bound to a narrow, sunlit strip of dry land and shallow water. The sunlit world we cherish is merely the surface film of a deep, watery planet. The warmth we feel, the brilliant colors we admire, and the clear views we take for granted are not the primary conditions of Earth. They are local privileges, granted by a thin atmosphere and a specific distance from our central star. Below us lies the true Earth, an immense, dark, high-pressure world that operates under its own harsh physical laws and harbors life forms so strange they challenge our very definition of biology. We are standing at the edge of the true terrestrial wilderness, where the light ends, the pressure builds, and the eternal darkness begins. As our submersible passes 200 meters into the ocean's depths, the faint indigo daylight fades into a grim, melancholic twilight. In this dimly lit borderland separating the sunlit world from total darkness, we encounter a planetary phenomenon so vast that it once confounded the world's most powerful militaries. The story began in the early 1940s during the height of World War II. The oceans had become intense tactical battlegrounds. American Navy destroyers patrolling the Pacific were hunting enemy submarines using newly developed sonar systems. These devices emitted high-frequency sound pulses down through the water column and analyzed the returning acoustic echoes bouncing off submerged objects or the seafloor. Sonar operators began recording an anomaly that defied basic geology. During daylight hours, their instruments consistently mapped a solid ocean floor at depths between 300 and 500 meters. The acoustic waves hit a dense mass and returned a clear echo, indicating a relatively shallow bottom. However, as twilight fell each evening, this apparent seafloor began to move. It detached itself from the depths, climbing steadily upward toward the surface. By midnight, the floor was near the top of the water column. As dawn approached, it sank back down into the gloom. For years, this classified phenomenon was dubbed the phantom bottom. Nautical charts were questioned, and naval captains were baffled. How could the solid floor of the ocean rise and fall by hundreds of meters in a strict 24-hour cycle? The mystery was solved when biological sampling revealed that sonar pulses were not reflecting off rock, sand, or mud. They were bouncing off trillions of air-filled swim bladders belonging to dense clouds of living organisms. The Navy had discovered the deep scattering layer, a massive living wall of flesh made up of billions of small fish, crustacea, jellies, and squids so tightly packed that they formed an acoustically impenetrable barrier. This phenomenon is known as diurnal vertical migration, the largest synchronized movement of biomass on Earth. It dwarfs the migrations of wildebeests across the Serengeti or caribou across the Arctic tundra. Every single night, billions of tons of deep-sea creatures ascend from the twilight depths to feed in the nutrient-rich surface waters, retreating back into the dark before daylight exposes them to visual predators. Leading this massive planetary migration is a small organism, the lanternfish. Hold a lanternfish in your hand, and it appears unremarkable. It rarely grows larger than a human finger, yet it is the undisputed titan of the open ocean's twilight ecosystem. Marine biologists estimate that lanternfish account for roughly 65% of all deep-sea fish biomass on Earth. If you were to collect and weigh every fish in the global ocean, more than half of that total weight would consist of lanternfish alone. They pass daylight hours floating in the dim twilight zone, deep enough to remain invisible to surface hunters like tuna, dolphins, and seabirds, but shallow enough to minimize energy expenditure. They maintain a state of suspended animation, waiting for the sun to sink below the horizon. When dusk arrives, the trigger is pulled. Lanternfish, alongside armies of copepods, krill, siphonophores, and squids, begin their ascent. They are chasing the microscopic plankton flourishing in the upper sunlit layers. This migration is a high-stakes gauntlet. If these creatures remain near the surface when dawn breaks, visual predators will decimate them. They must feed under the cover of dark and dive back down before the first morning rays illuminate the upper water column. Watching this event from a submersible at 300 meters looks like a blizzard in reverse. Millions of tiny bioluminescent bodies rush upward past the viewport in a silent, dense biological rush hour. This migration also acts as a major planetary metabolic engine. By consuming carbon-rich organic material at the surface and excreting it hundreds of meters down, these creatures trap vast quantities of carbon in the deep ocean, stabilizing Earth's atmospheric climate. Descending past this moving cloud of life, the sonar echoes clear. We pass through the false floor into deeper waters where the creatures do not migrate. They remain permanently in the cold, black silence. To truly understand the immensity of the deep scattering layer, one must appreciate the staggering physics governing this daily vertical journey. For a tiny creature no larger than a pinky finger, ascending 300 to 500 meters through the ocean column is the equivalent of a human running a full marathon straight up a vertical staircase twice every 24 hours. They perform this grueling physical feat on an empty stomach during the upward leg, fighting against localized fluid drag, shifting temperatures, and subtle changes in density. Why risk such immense energetic expenditure? Because the surface layer during the night represents an open-air buffet of astronomical proportions. During the day, sunlight powers the explosion of single-celled phytoplankton near the surface. These microscopic primary producers trap solar energy, multiplying by the billions. In turn, tiny zooplankton consume the phytoplankton, accumulating rich deposits of lipids, proteins, and essential fats. For deep-water animals living in a resource-scarce desert, the surface layer is a paradise of energy, if only they can reach it under the safety of darkness. As dusk approaches, the chemical and visual cues trigger the mass exodus. It does not begin with a vocal command or a visible signal, but with a silent, biological reaction to diminishing photons. As the sun dips toward the horizon, the faint downward shaft of blue light begins to weaken. The creatures in the twilight zone sense this subtle shift in light level using hypersensitive visual systems and pineal organs. They move upward, locking their position to a specific light intensity threshold, effectively following the fading sun's shadow as it retreats off the planet's surface. The sheer physical mechanics of the migration are a masterclass in biological engineering. Many species of lanternfish possess gas-filled swim bladders that act as precise buoyancy compensators. As they ascend through hundreds of meters of liquid, the ambient hydrostatic pressure drops significantly. Gas inside their tiny bladders expands rapidly according to fundamental pressure laws. To prevent their internal organs from rupturing or becoming too buoyant, which would shoot them helplessly to the surface like a cork, they must continuously reabsorb gas from the bladder into their bloodstream with extreme precision. When dawn approaches, the entire process reverses in a desperate, synchronized panic. As the very first rays of morning light hit the upper atmosphere, photons penetrate the surface water once again. To a lanternfish, light is a direct, deadly threat. Surface predators such as yellowfin tuna, oceanic white-tip sharks, swordfish, and pods of spinner dolphins possess sharp, daylight-adapted vision designed to spot the slightest motion or shadow from dozens of meters away. If a migrating organism is caught in the sunlit photic zone after dawn, its chances of survival drop to near zero. Thus, the downward plunge begins. Trillions of animals dive simultaneously, plunging back into the dim protection of the mesopelagic zone. They vent gas into their swim bladders to adjust to the crushing, steadily increasing pressure of the depths. By the time the sun fully rises over the horizon, the surface waters appear serene, blue, and empty, while hundreds of meters below, the false bottom has settled once again into a quiet, motionless layer of suspended life. This colossal daily movement of living weight acts as the planet's primary biological carbon pump, a critical process regulating the global climate system. When lanternfish and their fellow migrators gorge themselves on surface plankton, they consume vast quantities of organic carbon that was originally drawn out of the atmosphere by surface photosynthesis. As they dive back into the depths, they transport that carbon deep below the mixed surface layer. Down in the twilight zone, these animals metabolize their food, excreting nutrient-rich fecal pellets and releasing dissolved inorganic carbon through respiration. Because the cold, high-pressure water at these depths stays sequestered from the atmosphere for centuries, the carbon brought down by the deep scattering layer is effectively locked away from the atmosphere. Without this continuous, silent, vertical migration driven by trillions of tiny deep-sea animals, atmospheric carbon dioxide levels would be substantially higher, dramatically accelerating global planetary warming. Furthermore, the deep scattering layer serves as a vast, invisible nexus connecting the surface world to the mysterious abyssal plains below. Not all creatures that migrate make it back down alive, and not all carbon stays in the midwater. Deep-sea predators lie in wait along the bottom boundary of the twilight zone, operating like strategic ambushes at a mountain pass. Squid, dragonfish, and predatory jellies position themselves directly in the path of the migrating cloud, picking off individuals as they pass through the gauntlet. The organic waste, shed scales, and dead bodies resulting from this nightly feeding frenzy continuously fall deeper into the water column, generating a constant, slow-motion shower of nutrients known as marine snow. This drifting organic dust feeds the entire abyssal ecosystem miles below, sustaining bottom-dwelling worms, sea cucumbers, and deep-water scavengers that have never seen a single photon of sunlight in their entire evolutionary history. Thus, the deep scattering layer is far more than a historical military puzzle or a quirky sonar glitch from World War II. It is the beating heart of the open ocean's global metabolism. It is a vast, living pendulum swinging silently between light and darkness, pulling the energy of the sun deep into the cold, permanent night of planet Earth. As our submersible continues its plunge, passing through the clearing echoes of this biological wall, the last traces of the surface world disappear entirely, leaving us face to face with the permanent, unyielding darkness of the true deep sea. Descending past 200 meters down to 1,000 meters brings us into the mesopelagic layer, known as the twilight zone. Here, daylight vanishes completely. The water turns a cold, melancholic, uniform gray. In this zone, the primary struggle for survival is shaped by an economic crisis of light. The ambient downwelling sunlight is reduced to an absolute minimum, millions of times dimmer than the surface sun. Sunlight is no longer a source of heat or photosynthesis. It is a faint signal from an unreachable world. Down here, a single photon of light is a precious commodity. If an organism's eye can detect that lone spark of energy, it can spot the silhouette of prey above and survive. If it misses that photon, it starves or becomes food itself. This visual landscape has forced mesopelagic animals into an extreme evolutionary arms race of visual adaptations. One of the most extraordinary products of this visual arms race is Macropinna microstoma, the barrel-eye fish. At first glance, the barrel-eye fish looks like a surreal prototype built by an optical engineer. Looking at its face, you see a small, pouting mouth and two dark, indented holes where eyes would normally sit. For decades, scientists assumed those front holes were its eyes. They are actually olfactory organs, nostrils used to detect subtle chemical signatures in the water. To see its real eyes, you must look inside its head. The entire upper dome of the barrel-eye's skull is a clear, fluid-filled shield made of transparent tissue. Floating inside this biological canopy are two glowing green, barrel-shaped tubular eyes. These tubular eyes function like high-powered telescopic lenses, As the fish hovers in the gloom, those green barrels point directly upward through its clear skull, scanning the faint grey light above for the silhouettes of drifting siphonophores or jellies. For years, researchers assumed the barrel eye's eyes were fixed permanently upward. However, in 2009, scientists at the Monterey Bay Aquarium Research Institute captured live specimens using remotely operated vehicles. They discovered that when the fish detects prey, its tubular eyes rotate inside the clear dome, swiveling forward to lock onto the target as it maneuvers to strike. The transparent shield also serves as armor, protecting its delicate eyes from stinging tentacles when it picks food out of siphonophore colonies. Nearby, we find another optical specialist, Gigantura, the telescope fish. It features tubular eyes set on forward protruding stalks, resembling a pair of fixed binoculars. While most fish have eyes on the sides of their heads for a wide field of view, the telescope fish sacrifices lateral vision entirely. By pointing both tubular eyes forward, it gains overlapping binocular vision, granting it precise depth perception in near blackness conditions. It can mathematically gauge the exact distance to a faint, glowing target before striking with precision. To survive in a world where light is an absolute luxury, deep-sea organisms must stretch the physical limits of visual sensory biology far beyond what surface animals require. In the upper oceans, vision is taken for granted because photons are abundant and scatter in every direction. But in the mesopelagic realm, the visual landscape is reduced to an extreme exercise in statistical signal processing. The challenge is not merely gathering light, it is detecting a tiny handful of organized photons against a background of quantum sensory noise, thermal interference, and complete optical randomness. To extract every possible drop of information from this faint, downwelling glow, the eyes of mesopelagic specialists are packed with structural modifications. Unlike terrestrial eyes, which balance broad fields of view with color resolution, twilight eyes sacrifice color, spatial clarity, and wide-angle observation to achieve maximum sensitivity. The retinas of creatures like the barrellet and telescope fish are dominated almost exclusively by specialized rod cells, the photoreceptors responsible for processing low-light vision, while color-detecting cone cells are completely absent. These rod cells are not arranged in a single layer as they are in the human eye. Instead, deep-sea retinas feature multi-layered banks of densely packed rods stacked on top of one another like microscopic shelves. In some species, these retinal stacks are up to 6 or 7 layers deep. When an incoming photon passes through the lens and hits the retina, if it misses the first layer of rod cells, it travels into the second, third, or fourth layer beneath it. This structural stacking increases the mathematical probability that an incoming photon will collide with a visual pigment molecule and trigger a nerve impulse, ensuring that almost no light energy passing into the eye is wasted. Additionally, many mesopelagic species possess a tapetum lucidum, a specialized reflective mirror layer positioned directly behind the sensory retina. Made of tiny crystalline structures composed of guanine or specialized lipids, the tapetum acts as an optical retroreflector. When a photon travels through all the rod layers without being absorbed, it hits the reflective mirror of the tapetum and bounces straight back through the retinal stacks a second time. This doubling effect effectively gives the eye a second chance to catch every single photon entering the lens. In surface animals like cats or deer, the tapetum lucidum is what causes their eyes to shine in the beam of a car's headlights. In the twilight zone, this same mechanism transforms faint ambient gloom into readable visual contrast. The physical design of the lenses themselves is equally dramatic. To capture as much light as possible, mesopelagic animals possess disproportionately massive, perfectly spherical lenses. In human eyes, the lens is relatively flat and flexible, changing shape to focus on objects at varying distances. In the deep sea, a flat lens would let in far too little light. Spherical lenses act like wide-aperture camera objectives, gathering light from a vast area and concentrating it down onto a tiny, highly sensitive focal spot on the retina. However, large spherical lenses present a severe optical challenge known as spherical aberration, where light passing through the outer edges of the lens bends at a different angle than light passing through the center, producing a blurry, out-of-focus image. To solve this fundamental engineering flaw, deep-sea eyes feature graded index lenses. The density of the protein matrix inside the lens is not uniform. It is extremely dense at the center and becomes progressively softer toward the outer edges. This precise biological gradient bends light smoothly, regardless of where it enters the lens, projecting a crisp, focused image onto the retina, despite the extreme low-light conditions. This intense visual specialization creates a strange optical war between predator and prey. Animals operating in the mesopelagic layer are constantly balancing the need to see with the desperate necessity of remaining unseen. Because downwelling sunlight comes exclusively from directly overhead, the silhouette of an animal swimming above is its most dangerous vulnerability. A predator cruising below does not need to see the fine details of a prey item's scales or fins. It only needs to detect a dark, static shape breaking the faint, uniform indigo background of the sky above. This simple geometric reality dictates the movement, shape, and posture of almost every organism residing between 200 and 1,000 meters down. To minimize their visual signature, many fish in this zone have evolved compressed, razor-thin bodies. When viewed from the side, a hatchetfish or a dragonfish might look relatively large, presenting a broad surface area. But when viewed from directly below, the single angle from which visual predators hunt, their bodies are so narrow that they cast virtually no shadow at all. They become thin visual slivers, slicing through the water with minimal footprint. Furthermore, the green tubular eyes of Macropinna microstoma represent a hyper-specialized countermeasure against bioluminescent camouflage. The green lenses of the barrel contain specific fluorescent pigments that filter out specific wavelengths of downwelling blue light. This allows the barrel to distinguish between the natural, faint sunlight filtering down from the surface and the artificial bioluminescent light emitted by the belly photophores of prey species attempting to cloak themselves. The biological filter strips away the background noise, causing the disguised prey to stand out like a bright, stark silhouette against the filtered green glow. In addition to physical camouflage, the behavioral strategies of the twilight zone are deeply tied to this delicate visual balance. Many mesopelagic hunters remain completely motion-free for hours at a time, conserving their precious metabolic energy while hanging vertically in the water column. By maintaining a vertical posture, they reduce their horizontal profile, making themselves nearly invisible to anything searching from the side or below. They become living, floating tripwires, motionless sentinels waiting for the subtle disruption of light or water movement that signals the approach of a potential target. When an opportunity arises, the mechanics of the strike are executed with staggering speed and precision. In an environment where meals are separated by vast distances of empty water and hours or days of patient waiting, missing a prey item is an energetic catastrophe that can lead directly to starvation. The combination of enlarged, high-aperture lenses, multi-layered rod retinas, and specialized optical filters allows these deep-sea predators to calculate the precise distance, vector, and velocity of their prey before launching a single, decisive explosive strike. Beyond the specialized fish, invertebrate life in the twilight zone has evolved equally radical adaptations to exploit this low-light boundary. Glass squids, for instance, have made their entire bodies almost completely transparent to human and predator eyes alike, turning their organs into living crystal structures that allow downwelling photons to pass directly through them without scattering. The only visible parts of a glass squid are its dark, opaque eye bulbs and its digestive gland. To overcome this remaining visual vulnerability, the squid possesses specialized light-emitting organs mounted directly beneath its eyes, producing a subtle, downward glow that matches the intensity of the faint overhead skylight, effectively erasing the final shadows cast by its own internal organs. This continuous optical game of cat and mouse transforms the mesopelagic layer into one of the most sophisticated, high-stakes visual battlegrounds on planet Earth. Every adaptation, from the soft, fluid-filled canopy of the barrelé to the binocular stalks of the telescope fish, represents a brilliant evolutionary answer to the brutal physics of disappearing photons. As we continue to sink past the reach of the telescope fish and the barrelé, the downwelling sunlight grows dimmer still, fading from a readable indigo wash into a dark, featureless void where even the most sensitive eyes on Earth can no longer detect a single solar photon. We leave behind the realm of adapted vision and enter a domain where light is no longer borrowed from the sky, but manufactured entirely by life itself. Crossing the 1,000-meter mark carries us past the absolute limit of solar penetration, entering the bathypelagic zone, or the abyssal void. Here, the last vanishing photon of downwelling sunlight dies, and the ambient water temperature drops to a near-freezing 2 degrees Celsius. The hydrostatic pressure reaches hundreds of atmospheres, pressing inward with the weight of thousands of tons of liquid overhead. In this sunless expanse, sunlight is a distant memory, yet the dark is far from silent or dead. Instead, the abyss is illuminated by living light, bioluminescence. Bioluminescence is not a rare novelty in the deep ocean. It is the dominant form of communication, hunting, and defense on the planet. Over 90% of the organisms living in the bathypelagic layer are capable of producing their own cold, biological light through chemical reaction. Within specialized organs called photophores, a substrate molecule known as luciferin reacts with oxygen in the presence of an enzyme called luciferase. This reaction converts chemical bond energy directly into light with virtually 100% thermal efficiency, generating no waste heat. The predominant color of this living light is a brilliant blue-green. This is not accidental. Blue-green light possesses the specific wavelength, around 470 to 490 nanometers, that travels farthest through clear water with minimal absorption. Because deep-sea visual systems evolved to maximize sensitivity to this specific optical band, blue-green biological flashes can be seen across vast distances in the pitch-black water. Animals utilize this manufactured light in astonishing ways. The iconic deep-sea anglerfish, Melanocetus johnsonii, uses bioluminescence as a deadly trap. The female anglerfish features a modified dorsal fin spine that extends forward over her massive, tooth-lined mouth like a biological fishing rod known as the elysium. At the tip of this stalk rests a glowing organ called the esker, filled with symbiotic bioluminescent bacteria. In the total darkness, small fish and crustaceans are drawn toward the flickering glow like moths to a flame. As the unsuspecting victim approaches the light, the anglerfish expands her massive jaw, creating a sudden vacuum that snaps the prey inside backward-curving, needle-sharp teeth. Other creatures turn bioluminescence into an offensive weapon or a defensive smokescreen. The deep-sea dragonfish, Stomias boa, sports a glowing barbel hanging from its chin to attract prey, but it also possesses a far more sophisticated biological secret. While most deep-sea animals can only produce and see blue-green light, Certain species of dragonfish can generate a deep red light from photophores located beneath their eyes. Because almost no other creature in the bathypelagic zone can detect red wavelengths, this red beam acts as a secret night vision headlamp. The dragonfish can illuminate potential prey without alerting them to its presence, hunting in stealth mode while remaining completely invisible to the rest of the ecosystem. For prey species, light is used as a tool of deception and escape. When cornered by a predator, certain species of deep-sea shrimp do not release a cloud of dark ink like an octopus in shallow water. Instead, they spew a blinding cloud of glowing, bioluminescent fluid directly into the face of their attacker. The sudden explosion of brilliant light disorients the predator's sensitive, dark-adapted eyes, allowing the shrimp to kick backward and escape into the surrounding blackness. Similarly, the Atolla jellyfish uses bioluminescence as a biological burglar alarm. When seized by a predator, the Atolla does not fight back physically. Instead, it unleashes a dazzling, rotating strobe light pattern across its bell, flashing like an emergency beacon. This flash is not intended to scare off its captor, but rather to attract larger, secondary predators from hundreds of meters away. By signaling to the entire neighborhood that a meal is taking place, the jellyfish hopes a bigger hunter will arrive, attack its captor, and give it a chance to drift away unharmed. As we plunge deeper into the bathypelagic realm, the sheer physical pressure imposes extreme constraints on biological form and function. At a depth of 3,000 meters, the water pressure exceeds 300 times that at the surface, roughly 3 tons of force pushing down on every square inch of surface area. To survive these brutal conditions, deep-sea organisms have completely discarded air-filled cavities. Swim bladders, lungs, and delicate air spaces would collapse instantly under such force. Instead, their tissues are saturated with water and specialized fluid lipids, rendering their bodies virtually incompressible. Their cellular biology is equally modified. High hydrostatic pressure forces ordinary protein molecules to alter their shape and inhibits essential metabolic enzymes. To counteract this cellular crushing, deep-sea animals produce high concentrations of organic osmolytes, specifically trimethylamine N-oxide, TMAO. This compound binds tightly to water molecules, creating a rigid molecular shield that stabilizes proteins and cellular membranes against pressure-induced collapse. It is the presence of TMAO that gives deep-sea fish their characteristic, intense ocean smell when brought to the surface. In this extreme environment, food is extraordinarily scarce. Lacking direct sunlight for photosynthesis, the bathypelagic ecosystem depends entirely on organic debris falling from the sunlit upper layers, known as marine snow. This drifting material consists of dead plankton, fecal matter, shed exoskeletons, and organic dust. By the time this nutrient shower filters down through thousands of meters of midwater, over 99% of its energetic value has already been consumed by midwater organisms. Consequently, life in the bathypelagic layer operates on a starvation budget. Predators cannot afford to spend energy actively searching for prey across vast empty miles of water. Instead, they are built as low-energy ambushes. Many species have lost high-density muscle tissue entirely, replacing it with watery, gelatinous flesh that requires zero metabolic upkeep. Their metabolic rates are among the lowest ever recorded in the animal kingdom. A deep-sea fish may survive for months or even a year on a single, substantial meal. This metabolic conservation is reflected in bizarre, nightmare-like morphological designs. The gulper eel, Eurypharynx pelechinoides, possesses a tiny, ribbon-like body attached to a disproportionately massive jaw. Its loosely hinged mouth can unbutton and expand to several times the size of its own body, allowing it to swallow prey much larger than itself. Because encounters with potential food items are separated by weeks or months, the gulper eel must be physically capable of engulfing anything it meets, regardless of scale. Its stomach is similarly elastic, stretching to accommodate huge, rare meals in a desolate world where turning down a meal means ultimate extinction. Similarly, the fangtooth fish, an Hormenplagaster cornuta, boasts the largest teeth relative to body size of any fish in the ocean. The teeth on its lower jaw are so long that the fish cannot fully close its mouth. Instead, it possesses specialized biological sheaths on either side of its brain to slide the bottom fangs into, preventing the teeth from piercing its own skull when its mouth shuts. These horrific fangs do not chew or slice. They act as a living Iron Maiden, ensuring that once an unsuspecting victim is seized in the dark, escape is physically impossible. Living in these vast, sunless depths also creates an extraordinary reproductive challenge. When population densities are so low that two individuals of the same species might pass within a mile of each other only once in a lifetime, finding a mate is a monumental task. The humpback anglerfish has solved this problem through extreme sexual parasitism. The female anglerfish is a large, predatory creature, while the male is a tiny, dwarfed organism, born with an extraordinary sense of smell and zero ability to feed on his own. Upon hatching, the male anglerfish swims frantically through the dark, tracing the subtle pheromone trail released by a female. Once he locates her, he bites firmly into her belly. Over time, the tissue between their bodies fuses together, their circulatory systems merge, and the male's eyes, fins, and internal organs degenerate until he becomes nothing more than a permanent, living appendage on her side, receiving nutrients directly from her blood while providing a ready supply of sperm whenever she is prepared to spawn. To further navigate this vast void where visual contact is practically zero outside of short-range bioluminescent flashes, many deep-sea species rely on chemical and mechanical sensory networks that put terrestrial senses to shame. The lateral line system, a series of mechanoreceptive fluid-filled canals lining the sides of a fish's body, becomes hyper-developed in bathypelagic species. These sensory pores can detect the tiny displacement of water molecules caused by the faint fin flutter of a swimming organism dozens of meters away. In an environment where the background is dead quiet and motionless, any physical ripple through the liquid medium creates a distinct acoustic signature that alerts nearby predators to a potential target long before any light is generated. Furthermore, the biochemistry of deep-sea survival stretches far beyond structural T-MAO and bioluminescent enzymes. Because temperatures hover near freezing and pressure compresses molecular bonds, cell membranes in abyssal creatures face the risk of turning rigid and solid, much like warm butter hardening in a refrigerator. To maintain fluid, functioning cell walls, deep-sea organisms synthesize specialized unsaturated fatty acids with kinked molecular structures. These curved lipids fit loosely together within the cell membrane, preventing the structure from crystallizing under pressure and ensuring that critical molecular pumps and biochemical signals continue to function seamlessly across cellular boundaries. Even the skeletal structures of bathypelagic vertebrates reflect extreme adaptation to this high-pressure starvation regime. Bone is energetically expensive to construct and maintain, requiring calcium and phosphate ions that are difficult to extract from deep ocean water. Consequently, many deep-sea fishes have lost dense, calcified skeletons entirely, replacing them with light, cartilaginous frameworks or thin, paper-like spinal cords. This radical weight reduction gives them near-neutral buoyancy, allowing them to remain suspended in the water column without spending a single calorie of muscular energy to prevent themselves from sinking into the abyss. When large organic windfalls do occur, such as the massive corpse of a 70-ton blue whale sinking through thousands of meters of water to land on the barren seabed, it creates a localized energetic explosion known as a whale fall. A single whale fall can introduce more organic carbon to a specific patch of the seafloor than would normally fall from marine snow in 2,000 years. Within hours of the carcass landing, sleeper sharks, hagfish, and giant isopods arrive from miles away, using hypersensitive olfactory organs to detect the plume of decaying organic chemicals drifting through the currents. These initial scavengers strip the soft blubber and muscle tissues over months or years, tearing through the massive carcass with specialized, rasping mouthparts. Once the flesh is stripped, bone-eating. Osedax. Worms settle on the skeletal remains. These bizarre, root-like worms possess no eyes, mouth, or gut. Instead, they secrete acid to dissolve the mineral bone matrix, deploying symbiotic bacteria to metabolize the collagen and lipids trapped deep inside the whale's massive skeleton. A single whale fall can sustain a thriving, multi-tiered ecological oasis in the middle of the abyssal desert for over a century. As our submersible continues its plunge toward the abyssal plain 4,000 meters down, the eerie bioluminescent flashes become sparser. We are leaving behind the midwater column and approaching the vast, sediment-covered floor of the ocean basin, a realm of ancient mud, manganese nodules, and hydrothermally active fractures where life completely detaches itself from the sun, thriving, instead, on the raw chemical heat of the planet itself. As our journey plunges past the 1,000-meter threshold, we cross the definitive border into the bathypelagic zone, universally known to oceanographers and biological science as the midnight zone. Here, the last remaining trace of solar influence vanishes forever. There is no dawn, no dusk, no changing of seasons, and no lingering warmth. The ambient water temperature hovers at a constant, near-freezing point between 1 and 4 degrees Celsius. Yet, far more oppressive than the freezing cold or the absolute visual silence is an unseen, invisible tyrant that governs every single cubic millimeter of space in this realm: the physical tyranny of hydrostatic pressure. To understand the sheer magnitude of hydrostatic pressure, one must first understand how water behaves compared to air. On the surface of the Earth, human beings live at the bottom of an ocean of gas. The atmosphere presses down upon our bodies with a force of roughly 14.7 pounds per square inch, a physical baseline we define as 1 atmosphere of pressure. Because our internal tissues are composed primarily of solid and liquid structures, and because our lungs and internal cavities are filled with gas at that exact same pressure, we walk through our terrestrial world completely oblivious to the mass of air hovering above our heads. But liquid water is vastly denser than air, roughly 800 times denser. As you descend beneath the surface of the ocean, the weight of the water column accumulates with staggering speed. For every 10 meters of depth you sink, the hydrostatic pressure increases by another full atmosphere. By the time you descend to a depth of 1,000 meters at the ceiling of the midnight zone, the physical pressure surrounding your vessel has reached 100 atmospheres. That equates to roughly 1,500 pounds of relentless force pushing against every single square inch of surface area. If a conventional surface vessel or an unprotected hollow steel sphere were suddenly exposed to this depth, the atmospheric differential would cause an instantaneous, catastrophic structural failure. The air inside would be compressed in a microsecond, imploding the metal structure with the force of an explosion, generating enough frictional heat to briefly ignite the air inside before the freezing water flooded the void. Human expeditions into this realm require custom-engineered spherical pressure hulls, forged from forged titanium or ultra-thick acrylic, built specifically to resist a pressure force capable of bending and warping thick industrial steel plates. Yet, as extreme as 1,500 pounds per square inch sounds, the midnight zone continues downward for another 3,000 meters. At 4,000 meters depth, near the abyssal floor, the pressure mounts to an astonishing 400 atmospheres, over 6,000 pounds per square inch. This is the equivalent of balancing a heavy luxury automobile on the tip of your thumb. It is a physical force so intense that it fundamentally alters the physics and chemistry of matter itself. At these immense depths, pressure ceases to be merely a structural threat to hollow objects. It becomes a biochemical assault on the very molecular mechanics of life. In the surface world, water is often described as an incompressible fluid, but under hundreds of atmospheres of pressure, even liquid water molecules are forced slightly closer together, altering the hydrogen bonds that give water its unique chemical properties. For an ordinary surface organism dropped into this environment, the damage would not just be crushed lungs or collapsed air cavities. The true fatal blow would occur at the cellular and molecular level. Under high hydrostatic pressure, ordinary biological proteins, the complex molecular machines responsible for muscle contraction, metabolic energy production, and cellular repair, are physically squeezed and distorted out of shape. Proteins rely on delicate, three-dimensional folding patterns maintained by weak chemical bonds. When exposed to hundreds of atmospheres, the surrounding water molecules are forced into the interior pockets of these proteins, causing them to unfold, lose their structural integrity, and cease functioning entirely. Enzymes stall, cellular transport stops, and metabolic pathways collapse into total stasis. Furthermore, the delicate lipid bilayers that form cell membranes, which must remain fluid and flexible to allow nutrients and signals to pass into the cell, undergo a physical phase transition. Under high pressure and cold temperatures, ordinary cell membranes harden and solidify like liquid oil turning into hard wax in a freezer, rendering the cell rigid, brittle, and incapable of life. How then do the native inhabitants of the midnight zone exist, thrive, and hunt in an environment defined by such molecular tyranny? The answer lies in millions of years of profound, radical biochemical evolution. Deep-sea organisms do not fight hydrostatic pressure, they internalize it, balancing their internal biochemistry so perfectly with the external physical forces that they become completely immune to the crushing weight of the sea. To prevent their proteins and enzymes from collapsing under extreme pressure, bathypelagic creatures produce high concentrations of specialized organic molecules known as piezolites, most notably trimethylamine N-oxide, commonly abbreviated as TMAO. TMAO acts as a chemical scaffolding or a molecular anchor within the cell. It binds tightly to surrounding water molecules, forcing them into a rigid, organized hydration shell around biological proteins. This protective barrier prevents pressurized water molecules from invading the interior folds of enzymes, allowing proteins to maintain their functional three-dimensional shapes, even under hundreds of atmospheres of crushing weight. The deeper a fish lives, the higher the concentration of TMAO it must maintain within its muscles and tissues to survive. To overcome the threat of frozen, rigid cell membranes, deep-sea organisms engage in homeoviscous adaptation. Their biological membranes are constructed with unusually high concentrations of polyunsaturated fatty acids. These specialized lipid molecules feature bent, kinked molecular tails that prevent them from packing tightly together under high pressure. This structural elasticity keeps the cell membranes fluid, flexible, and fully operational at temperatures near freezing and under forces that would solidify the cellular walls of any surface dweller. Furthermore, life in the midnight zone has completely abandoned the use of gas as a structural or functional medium. Gas expands and contracts violently with changing pressure, making bladders and lungs dangerous liabilities in a vertical ocean column. Instead, bathypelagic fish have replaced gas-filled swim bladders with lipid-rich organs, dense gelatinous deposits, or watery tissue matrices that are naturally incompressible. Because their bodies are composed entirely of liquids and solids that exist at the exact same hydrostatic pressure as the surrounding ocean, there is no pressure differential pushing inward. A deep-sea fish living at 4,000 meters feels no more crushed by the ocean overhead than a human walking through a sunlit meadow feels crushed by the atmosphere. They move through the crushing dark with fluid, effortless grace, completely oblivious to the thousands of tons of liquid weight resting above their fragile bodies. Enclosing over 70% of the total living volume of the global ocean, the Midnight Zone is by far the largest single habitat on planet Earth. It is a vast, three-dimensional oceanic wilderness that stretches unbroken across thousands of miles of longitude and latitude. Yet, despite its colossal spatial dimensions, it is an environment defined by absolute resource scarcity. In this sunless abyss, there are no photosynthetic plants, no green pastures, and no solar-fueled blooms. Energy arrives only as a sparse, unpredictable trickle falling from the world above. To survive in this vast, dark desert, the organisms of the Midnight Zone operate on the most conservative metabolic budget in the biological world. They do not waste energy on fast swimming, heavy bone structures, or constant territorial defense. Many species have discarded dense skeletal frameworks entirely, evolving soft, cartilaginous spinal cords and water-saturated, jelly-like flesh that requires virtually zero metabolic maintenance. They drift through the blackness like living phantoms, suspended in near-neutral buoyancy, waiting with infinite patience for a rare encounter with something edible. It is within this quiet, high-pressure void that evolution has crafted one of the most brilliant and visually counterintuitive biological illusions in the natural world: the paradox of the scarlet camouflage. If you were to illuminate a collection of deep-sea animals brought up from the Midnight Zone with a bright white halogen flashlight, you would be immediately struck by a shocking visual realization. A vast majority of the creatures inhabiting this sunless depth, from delicate deep-sea shrimp, amphipods, and pelagic crabs to glass squids, floating medusae, and predatory fish, are not dull black or transparent gray. They are painted in brilliant, vivid, saturated shades of crimson, ruby red, and bright scarlet. To a human observer accustomed to the sunlit world, this brilliant red coloration seems like an evolutionary absurdity. In a dark room, or against a dark background, a bright scarlet animal stands out like a shining flare. On land or in shallow coastal waters, bright red is an aggressive, high-visibility signal used by toxic frogs to warn off predators, or by exotic birds to attract mates across dense green foliage. Why would evolution paint fragile, defenseless creatures living in a pitch-black abyss in the most vibrant, fiery color imaginable? Why would a deep-sea shrimp or a delicate squid wear a blazing red suit in a world where remaining unseen is the absolute prime directive of survival? The answer to this mystery is a masterclass in optical physics and spectral attenuation. The secret lies in the fundamental behavior of light as it travels through liquid water. As established earlier in our descent, sunlight is composed of a broad spectrum of visible electromagnetic wavelengths, ranging from long, low-energy red waves around 700 nanometers down to short, high-energy blue and violet waves around 450 nanometers. Liquid water molecules absorb light energy with extreme selectivity, stripping away wavelengths based on their energy levels. Because red light possesses the longest wavelength and the lowest energy of any visible color, it is absorbed by liquid water far more aggressively than any other part of the spectrum. When sunlight strikes the surface of the open ocean, the red component of the spectrum begins dying instantly. Within the first 5 to 10 meters of the surface, over 90% of all red light photons are absorbed by water molecules and converted into thermal kinetic energy. By the time you reach a depth of just 30 to 40 meters, red light has been completely erased from the natural water column. Below 100 meters, there is not a single photon of red sunlight left in existence anywhere on planet Earth. This physical reality radically transforms the nature of color perception in the ocean. Color is not an inherent, intrinsic property of an object. It is merely the specific wavelength of light that reflects off an object's surface and strikes an observer's eye. A bright red apple appears red on land because when white sunlight hits the skin of the apple, the chemical pigments in the skin absorb blue, green, and yellow light while reflecting red light back into your visual cortex. If you take that same red apple into a dark room and shine a pure blue or green light onto it, there are no red photons available for the skin to reflect. The apple completely absorbs the blue and green light, reflecting nothing back to your eyes. Under pure blue illumination, the bright red apple appears instantly, undeniably, jet black. Now, consider the optical environment of the twilight and midnight zones. The only natural sunlight that penetrates into the deep sea consists of a faint, heavily filtered beam of pure blue-green light, centered around 480 nanometers. Furthermore, over 90% of all bioluminescent light produced by deep-sea organisms is manufactured in that exact same narrow blue-green optical band, because blue-green light travels farthest through seawater without being absorbed. In an environment where the only light in existence is pure blue-green, wearing a bright scarlet skin is the ultimate form of stealth technology. When a predator emitting a blue-green bioluminescent flash sweeps its light across a crimson deep-sea shrimp or a scarlet squid, the biological pigments on the prey's body behave like a total optical black hole. The red pigment absorbs every single blue-green photon that strikes it, reflecting absolutely zero light back into the predator's eyes. To any creature hunting in the deep sea with standard low-light vision, a bright scarlet animal does not look red. It looks as dark, flat, and invisible as soot on a charcoal brick. It blends so perfectly into the surrounding pitch-black water that it disappears entirely, casting no highlight and leaving no visual trace. This optical illusion provides deep-sea organisms with a massive evolutionary advantage over animals that are painted in pure black pigment. Producing dense, dark melanin pigments requires a significant investment of metabolic energy and scarce dietary nitrogen, resources that are extremely hard to come by in a starvation budget ecosystem. On the other hand, red carotenoid pigments can be easily acquired from consuming microscopic marine snow, planktonic debris, or copepods that have filtered surface organic matter. By incorporating these readily available carotenoid compounds into their exoskeletons, skins, and shells, deep-sea creatures achieve flawless, absolute visual invisibility at a fraction of the metabolic cost. Consider the case of the strawberry squid, Histiotuthis heteropsis, a surreal inhabitant of the mesopelagic and bathypelagic layers. The strawberry squid derives its common name from its shocking appearance when brought to the surface under bright lights. Its entire body is a brilliant, glowing strawberry red, covered in small, dark, luminescent dots that look precisely like tiny seeds. In its natural, deep water habitat, that brilliant red skin absorbs every stray photon of ambient blue light, rendering the squid completely invisible to larger predators cruising below. Meanwhile, those tiny seed-like photophores on its underside produce precise, downward-directed blue bioluminescence, erasing its own silhouette against the faint, downwelling skylight above through counter-illumination. The red pigment hides it from the sides and top, while its glowing belly photophores hide it from below, creating a complete, multi-layered cloak of optical invisibility. Similarly, deep-sea shrimp, such as Acanthophera purpurea, display intense, uniform crimson coloration across their entire bodies. When threatened by a fast-approaching predator, these shrimp combine their scarlet optical camouflage with an explosive active defense. They eject a bright, glowing cloud of blue, bioluminescent liquid directly into the face of their attacker. As the predator is blinded by the sudden blue glare, the shrimp uses its muscular tail to snap backward into the dark. Because its crimson body absorbs the blue light generated by its own chemical decoy, the shrimp instantly vanishes from sight, leaving the predator snapping at a cloud of empty, glowing water. For tens of millions of years, this scarlet camouflage reigned supreme as an unbroken, invincible stealth technology throughout the world's deep ocean. But in the relentless, perpetual arms race of evolutionary biology, no defense remains unbreached forever. Eventually, a predator emerged that cracked the scarlet code, breaking the optical rules of the deep sea and turning the invisible crimson prey into bright, easy targets. That predator is the legendary deep-sea dragonfish, specifically members of the family Malacostidae, such as the stoplight loosejaw, Malacosteus niger. While almost every other organism in the midnight zone evolved eyes that can see only blue-green light and photophores that produce only blue-green light, the dragonfish developed a brilliant, revolutionary optical loophole. Beneath its large, terrifying eyes, the dragonfish possesses specialized bioluminescent organs that generate a deep, vibrant, long-wavelength red light, a biological night vision headlamp that operates around 700 nanometers. To produce this red beam, the dragonfish uses a complex biological filter system. Its internal photophores first manufacture a standard blue-green light, but this light is immediately passed through a thick, red-pigmented fluorescent filter before exiting the body. This filter converts the high-energy blue-green light into a long, deep red beam that shines out into the dark water directly in front of the dragonfish's jaws. Simultaneously, the dragonfish modified its own visual architecture to perceive this secret wavelength. Its retinas contain specialized visual pigments, supplemented by dietary chlorophyll derivatives that allow its eyes to detect red light with exceptional sensitivity. The ecological consequence of this evolutionary breakthrough is absolute devastating tactical superiority. As the dragonfish cruises through the bathypelagic dark, it shines its invisible red headlight into the blackness. Because no other deep-sea animal can see red light, the dragonfish can sweep its searchlight across potential prey, rival predators, and mates without giving away its own position. It remains completely invisible to the rest of the ecosystem, and when that secret red beam hits a bright scarlet deep-sea shrimp, a crimson crab, or a strawberry squid, the scarlet camouflage fails instantly. Because there are now red photons striking the red pigment of the prey's body, the red surface reflects those photons straight back into the dragonfish's specialized eyes. The once invisible scarlet prey, floating peacefully in what it believed to be safe, absolute blackness, suddenly ignites like a bright, glowing target under the dragonfish's private night vision beam. Before the prey even realizes it has been illuminated, the dragonfish unhinges its specialized, flawless jaw and snaps its needle-sharp fangs shut around its meal. In the sunless expanses of the midnight zone, life is a constant, high-stakes game played at the absolute edge of physical and biological possibility. Under the crushing tyranny of hundreds of atmospheres of hydrostatic pressure, where proteins face structural collapse and cell membranes threaten to solidify into ice, evolution has engineered biochemical miracles to keep the spark of life burning. And in the visual void, where sunlight is nothing more than an ancient memory, the battle for survival is waged with manufactured photons, optical filters, and deceptive crimson cloaks. It is an alien world operating under its own uncompromising rules, where beauty is forged in absolute dark, and where being painted in the color of fire is the single best way to stay completely invisible. Descending into the abyssal depths past 1,000 meters, the physical rules that govern surface biology break down completely. In this sunless, high-pressure wilderness, organisms cannot rely on simple speed, raw physical strength, or broad visual sweeps to survive. Instead, evolutionary adaptation becomes a refined discipline of precision engineering, biochemical alchemy, and biological teamwork. To understand how life conquers an environment where every calorie is a hard-won prize and every photon is an engineered weapon, one must examine three of the most astonishing evolutionary miracles in the ocean's depths: the terrifyingly advanced optical warfare of the stoplight loose-jaw dragonfish, the horrific yet effective reproductive strategy of the humpback anglerfish, and the primordial biological engine that powers both: bacterial symbiosis. In the perpetual midnight of the bathypelagic zone, almost every creature that possesses vision has tuned its eyes to a single, narrow band of the light spectrum, blue-green light, centered between 470 and 490 nanometers. Blue-green light is the only wavelength that travels any significant distance through dense, liquid seawater without being rapidly absorbed. Consequently, deep-sea organisms produce blue-green bioluminescence to signal mates, lure prey, or startle attackers, and their visual systems have evolved to be hypersensitive exclusively to these blue-green photons. Red light, with its long wavelength and low energy, is absorbed by seawater within a few meters, making it utterly non-existent in the deep ocean under normal natural conditions. Because no red light ever reaches these depths, virtually all deep-sea animals are completely blind to red wavelengths. Enter Malacosteus niger, the stoplight loose-jaw dragonfish. This small, slender predator has engineered a biological loop that shatters the optical rules of the deep sea, effectively granting itself a secret, private sniper scope in total darkness. Mounted directly beneath each of its massive eyes, the stoplight loosejaw possesses a specialized, oval-shaped light organ known as a photophore. While most deep-sea creatures use photophores to flash blue or green, the loosejaw's suborbital photophore produces a deep, saturated red light at approximately 700 nanometers. To achieve this, the fish first manufactures bioluminescent light internally through a standard chemical reaction. It then passes these photons through an extraordinary internal optical filter composed of dense, dark red fluorescent pigments. This filter absorbs the shorter, energetic wavelengths and re-emits the light as a pure beam of deep red. Simultaneously, the loosejaw modified its retina to perceive its own custom beam. In ordinary deep-sea fish, the retinal photoreceptors contain a single visual pigment, tuned strictly to blue-green light. The stoplight loosejaw, however, incorporates a derivative of chlorophyll, a compound absorbed directly from its diet of deep-sea copepods, into its retinal cells. This specialized sensory pigment acts as a photosensitizer, absorbing long red photons and transferring that energy to the visual nerve cells. The tactical advantage of this adaptation is absolute. As the loosejaw glides through the pitch-black water, it shines a beam of red light ahead, like an invisible night vision flashlight. Because every other organism in its habitat is blind to red light, prey animals have no idea they are standing inside a bright spotlight. They do not swim away. They do not trigger defensive responses. They sit motionless in what they perceive to be safe, total darkness. Meanwhile, the loosejaw sees them clearly. Even more terrifyingly, creatures that use scarlet or crimson pigmentation as camouflage, relying on the fact that red surfaces absorb ambient blue light to appear jet black, are betrayed instantly. Under the loosejaw's red searchlight, their crimson bodies reflect the red photons straight back into the hunter's eyes, causing them to glow like bright targets in an empty sky. The loose jaw's offensive engineering does not stop at its eyes. Its common name derives from its astonishing, nightmare-like jaw apparatus. In ordinary fish, the bottom of the mouth is closed off by a muscular floor and membrane, which creates suction when the mouth snaps open to pull water and prey inside. But in the deep ocean, dragging a wide, fleshy mouth floor through dense water creates hydrodynamic drag, slowing down the jaw's forward strike and warning the prey through pressure waves. The stoplight loose jaw solved this fluid dynamic problem by eliminating the floor of its mouth entirely. Its lower jaw consists of nothing more than a thin, curved, unhinged strut of jawbone equipped with long, curved, needle-sharp teeth. There is no muscle tissue, no skin, and no fleshy floor connecting the sides of its lower jaw. When the loose jaw strikes, its open, flawless jaw slices through the high-pressure water with virtually zero drag, swinging forward like a biological bear trap at blinding speed. Once those needle fangs puncture the target, there is no escape. The prey is swung backward, directly into the fish's throat, where specialized pharyngeal teeth drag it down into the stomach. While the stoplight loose jaw relies on active optical stealth, another resident of the Midnight Zone has mastered the art of passive ambush through biological deception. Melanocetus johnsonii, the iconic humpback anglerfish. Living at depths between 1,000 and 3,000 meters, the female humpback anglerfish is a walking study in extreme biological conservation. Her body is spherical, dark brown or jet black, and largely composed of soft, water-dense tissue rather than heavy muscle or dense bone. In an environment where meals may be separated by weeks or even months, maintaining high-density muscle mass would lead to swift starvation. Instead, she hovers almost motionlessly in the water column, operating as a living, waiting trap. Dorsal evolution has transformed her anterior dorsal fin spine into a flexible, extended fishing rod, known as the iliceum, which hangs forward directly over her enormous, gaping mouth. At the terminal tip of the iliceum rests a soft, bulbous flesh organ called the esker. The esker is a living lantern, glowing with a soft, persistent light in the pitch-black void. Unsuspecting crustaceans, squids, or small fish swimming through the empty dark spot this solitary, flickering light and approach, mistaking it for a small, edible prey item or a potential mate. As the curious target drifts within striking distance, the female anglerfish expands her massive, highly elastic buccal cavity. This sudden expansion creates an intense localized vacuum, snapping the victim inside a cavernous mouth lined with long, sharp, inward-curving teeth that fold inward to allow entry but lock rigid to prevent escape. Yet, as impressive as her hunting apparatus is, the most radical evolutionary pressure acting on the humpback anglerfish is not finding food, it is finding a mate. In the vast, three-dimensional void of the bathypelagic zone, population densities are unimaginably low. Two anglerfish might pass within 100 meters of each other only once in their entire lifetimes. If a male and a female met and simply mated before swimming away, the probability of either individual ever finding another partner to reproduce with again would be practically zero. Evolution solved this catastrophic demographic hurdle through one of the most extreme reproductive strategies in the animal kingdom: obligate sexual parasitism. Female anglerfish grow relatively large, sometimes reaching the size of a basketball, but male anglerfish are microscopic dwarfs by comparison, rarely growing larger than a human fingernail. The male is not built to hunt. He possesses no lure, no massive teeth, and a severely underdeveloped digestive system. From the moment he hatches, his biological clock is ticking rapidly towards starvation. He is born for a single purpose: to find a female before his tiny energy reserves run out. To aid his desperate search, the male anglerfish is equipped with two hyper-specialized sensory systems. His eyes are disproportionately large, designed specifically to detect the faint, unique flash pattern of a female's glowing esker from dozens of meters away in the dark. Even more importantly, his nostrils are massive, housing hypersensitive olfactory organs capable of detecting microscopic pheromone trails released by the female into the ocean currents. The male swims frantically through the dark, tracing the chemical gradient left by a female. When he finally locates her, he does not perform a courtship display. He immediately swims up to her underbelly, opens his tiny mouth, and bites firmly into her soft skin. What happens next borders on science fiction. The male's jaws release specialized digestive enzymes that dissolve the outer skin of his own lips and the corresponding patch of tissue on the female's belly. As the tissues break down, the male's body begins to fuse at a cellular level with the female. Their skin cells knit together, and their circulatory systems physically merge. The blood vessels of the female grow directly into the body of the male, supplying him with oxygen, lipids, glucose, and essential nutrients directly from her bloodstream. Over the following weeks, the male's body undergoes total degeneration. Because he no longer needs to swim, hunt, see, or digest food, his eyes wither, his fins atrophy, his internal organs dissolve, and his mouth permanently fuses to her flesh. He ceases to exist as an independent animal. He becomes nothing more than a living, blood-fed organ attached to the female's side, a permanent, on-board sperm factory. When the female's hormones signal that she is ready to release her egg rafts into the water, she sends a hormonal cue through her blood directly into the attached male, triggering him to release his sperm simultaneously. A single female can play host to multiple parasitic males fused to her body, ensuring that whenever she is ready to spawn, she carries an ever-present, guaranteed supply of genetic material in the middle of a vast, empty wilderness. Whether examining the glowing esker of the humpback anglerfish, the luminous belly photophores of the strawberry squid, or the colossal ecosystems surrounding hydrothermal vents on the abyssal plain, one fundamental biological truth becomes clear. Deep-sea animals rarely generate their own survival tools in isolation. At the core of the deep ocean's most complex adaptations lies a microscopic master partner: bacterial symbiosis. In the case of the humpback anglerfish and many other bioluminescent species, the animal itself does not possess the genetic code or cellular machinery required to produce light. The glowing esker dangling at the end of the anglerfish's rod is not a light bulb made of fish tissue. It is a highly specialized biological incubator housing billions of luminescent, single-celled bacteria belonging primarily to the family Vibrionaceae. This relationship is a mutualistic partnership forged over millions of years of coevolution. The female anglerfish provides her bacterial guests with a pristine, controlled environment inside the pore-lined chamber of the esker. Her blood vessels wrap tightly around the light organ, continuously delivering a steady supply of oxygen, amino acids, and vital nutrients to fuel the microbe's metabolism. In return, the bacteria perform a continuous, cold chemical reaction known as bioluminescence. Inside each bacterium, a specialized enzyme called luciferase catalyzes the oxidation of a substrate molecule called luciferin alongside a reduced flavin mononucleotide, BuFMNH, $2. As oxygen breaks the chemical bonds of the luciferin molecule, the extra chemical energy is released not as heat, but as steady, brilliant photons of light. The anglerfish exercises control over this light by altering the blood flow to the esker. By constricting her blood vessels and starving the bacteria of oxygen, she can dim or turn off the glow, pulsing her light lure like a flickering beacon to entice curious prey. This biological partnership is so profound that a young, newly metamorphosed female anglerfish is born with a completely dark, sterile esker. She cannot produce a single spark of light on her own. As she descends into the deep ocean, The empty pore at the tip of her elysium remains open to the surrounding seawater. She sweeps her lure through the water column until she draws in free-living luminescent bacteria floating in the deep water. Once the correct bacterial strain enters the esca's inner chamber, the pore seals shut or restricts entry, and the bacteria begin to multiply rapidly, establishing a permanent, glowing colony that will illuminate the hunter's traps for the rest of her life. Beyond the realm of light and hunting, bacterial symbiosis plays an even more foundational role on the ocean floor. It serves as the ultimate primary producer for entire sunless worlds. Thousands of meters below the surface, where the Earth's crust splits open at tectonic boundaries, hydrothermal vents spew towering plumes of mineral-rich water, heated to over 400 degrees Celsius. This vent fluid is heavily laden with toxic chemicals, most notably hydrogen sulfide, a substance lethal to almost all complex animal life. Yet, surrounding these volcanic chimneys are dense, thriving cities of giant tube worms, Riftia pachyptila, vent shrimp, and blind crabs. These deep-sea ecosystems exist entirely without sunlight because bacteria have replaced plants as the base of the food chain. Through a process called chemosynthesis, specialized chemotrophic bacteria absorb toxic hydrogen sulfide, carbon dioxide, and oxygen from the vent fluids. By breaking the chemical bonds of hydrogen sulfide, these microbes extract chemical energy, using it to synthesize organic carbon molecules, sugars, proteins, and fats in complete darkness. The giant tube worm, Riftia pachyptila, has taken this bacterial relationship to its absolute evolutionary extreme. Riftia. Worms grow up to 8 feet long inside white chitinous tubes, topped with vibrant crimson plumes. Yet, an adult tube worm has no mouth, no eyes, no gut, no anus, and no digestive tract of any kind. It is physically incapable of eating food. Instead, over half of the worm's internal body volume is occupied by a massive, highly vascularized organ called a trophosome, which is packed with billions of symbiotic chemosynthetic bacteria. The worm's vibrant red plume is filled with a unique, oversized hemoglobin molecule that binds both oxygen and toxic hydrogen sulfide simultaneously, carrying them safely through the worm's bloodstream without poisoning its own tissues. The blood delivers these raw chemicals directly to the trophosome, where the internal bacteria process the sulfide, manufacture rich organic carbon, and secrete those nutrients directly into the worm's bloodstream. The worm feeds the bacteria raw geothermal chemicals, and the bacteria feed the worm life-sustaining energy. From the optical night vision searchlights of the stoplight loosejaw dragonfish to the parasitic male anglerfish fused forever to his glowing mate, down to the microbial engines driving life at the bottom of the world, the deep ocean proves that life is not defined by the presence of sunlight. Under thousands of pounds of crushing pressure and in eternal darkness, evolution does not merely survive, it flourishes, engineering complex, astonishing solutions to the absolute limits of existence. As we push deeper into the vast, sunless expanse of the deep ocean, every biological system is forced to confront the single most brutal reality of the abyssal realm: absolute, unrelenting starvation. In the surface waters, the sun drives massive blooms of phytoplankton, fueling dense food webs of fish, marine mammals, and oceanic predators. But as you descend beneath the photic zone, that vibrant solar engine disappears entirely. Down here, in the cold midwaters thousands of meters below the surface, there are no plants, no algae, and no direct sources of primary biological production. Life is forced to subsist entirely on whatever organic scraps happen to fall from above. This drifting shower of biological debris, known to science as marine snow, consists of decaying plankton, shed exoskeletons, fecal matter, and organic dust. But By the time this shower filters down through thousands of meters of water, over 99% of its nutritional value has already been devoured by the creatures living in the upper layers. What reaches the bathypelagic zone is little more than a sparse, nutrient-depleted dust, leaving the inhabitants of the deep to navigate an environment of perpetual energy poverty. To survive in a world where a single square meal might be separated by weeks, months, or even a year of total emptiness, deep-sea organisms have been forced to adopt the most conservative metabolic strategies on planet Earth. On the surface, predators spend massive amounts of energy actively swimming, patrolling vast territories, maintaining high body temperatures, and building dense, powerful muscle tissue. In the bathypelagic zone, such energy expenditure is a quick path to immediate extinction. A deep-sea fish that spends its calories actively chasing prey across miles of empty water will burn through its internal reserves long before it ever encounters another living creature. Thus, evolution has stripped away the energetic luxuries of surface life, re-engineering abyssal creatures into low-energy ambushes that operate on a strict starvation budget. This metabolic conservation manifests in radical structural changes. Deep-sea fishes have largely abandoned dense, heavy muscular systems, replacing firm muscle fibers with watery, gelatinous tissue that requires almost zero caloric upkeep to maintain. They have discarded thick, calcified skeletons, evolving thin, flexible cartilaginous frameworks or papery spinal cords that drastically reduce their reliance on scarce minerals and energy-intensive bone maintenance. Furthermore, by matching their body density to the surrounding seawater through high fluid lipid concentrations, these animals achieve near-neutral buoyancy. They do not need to burn fuel swimming against gravity to keep from sinking into the abyss. Instead, they hover weightlessly in the pitch-black water column, hanging like motionless specters in the dark, waiting with infinite patience for the universe to send a rare calorie their way. This extreme starvation strategy reshapes not only how these creatures hold themselves in the water, but how their very cells process life. The basal metabolic rates of deep-sea bathypelagic animals are among the lowest ever measured in the animal kingdom, often hundreds of times lower than those of shallow water species of similar size. Their hearts beat with sluggish, agonizing slowness, their cellular repair mechanisms operate at a crawl, and their respiratory systems consume oxygen at a fraction of the rate seen in surface animals. Every physiological process is dialed down to the absolute bare minimum required to maintain life. They live in a state of suspended animation, conserving every microjoule of energy, converting their bodies into hyper-efficient biological vaults designed to stretch the energy of a single meal across an entire season of sunless isolation. Yet, living on a starvation budget creates an inescapable evolutionary dilemma when an encounter with potential prey does finally occur in the vast black void you cannot afford to miss. In a world where food is exceptionally rare, turning down a meal because it is too large or awkwardly shaped is a luxury no bathypelagic predator possesses. If a starving predator encounters a prey item that happens to be twice its own size, it must find a way to capture, overpower, and consume that prey, or face ultimate starvation before another opportunity presents itself. This relentless evolutionary pressure has birthed some of the most bizarre, nightmare-like morphological adaptations in the animal kingdom, nowhere more strikingly illustrated than in the formidable structure of the gulper eel, scientifically known as Eurypharynx pelicanoides. The gulper eel looks less like a traditional fish and more like a feverish hallucination of deep-sea engineering. At first glance, its body appears impossibly disproportionate. It possesses a long, thin, ribbon-like tail that tapers away into the darkness, completely devoid of heavy swimming muscles or traditional scales. But attached to this delicate, whip-like body is a head and jaw apparatus of gargantuan proportions. The skull and jaws of the gulper eel account for a massive percentage of its total body mass, featuring a mouth that can open to a size many times larger than the rest of its entire body combined. The jaw architecture of the gulper eel is a masterclass in extreme anatomical modification. In ordinary fishes, the jaw bones are firmly anchored to the skull, limiting the angle to which the mouth can open. In the gulper eel, however, the jaw hinges are loosely jointed and set far back along the head, allowing the lower jaw to unbutton and drop downward like a cavernous biological net. Between the extended jaw struts lies a vast, elastic pouch of thin skin, similar to the pouch of a pelican. When the gulper eel approaches a target, it swings its jaw wide open, expanding this massive buccal pouch into a wide, gaping funnel. As it lunges forward, the funnel scoops up vast volumes of water, along with whatever luckless creature happens to be inside, from schools of small crustaceans to squids and fishes far larger than the eel's own slender torso. Once the prey is scooped inside the gaping pouch, the gulper eel faces a secondary physical challenge, dealing with the sheer volume of trapped water. Swallowing a massive net full of water would overwhelm its internal organs and severely restrict its mobility. To solve this, the eel gently compresses its elastic pouch, forcing the excess water out through its specialized gill slits while keeping the solid prey trapped inside. The eel's teeth are tiny and inward curving, designed not to chew, tear, or crush flesh, but to act as a one-way biological rake that prevents the prey from squirming backward out of the mouth. Following the jaw comes an equally miraculous digestive adaptation, a stomach capable of unprecedented physical expansion. The stomach of the gulper eel is composed of hyperelastic muscular walls and specialized connective tissue that can stretch to accommodate prey items that dwarf the eel's rest state. When a large meal is swallowed, the stomach inflates like a rubber balloon, distorting the eel's body shape into a strange, engorged sphere. Inside this stretched organ, powerful digestive juices go to work, slowly breaking down the massive windfall of organic matter over days and weeks. A single massive capture processed inside this expanding vault can supply the gulper eel with enough metabolic energy to survive for months without needing to strike again. To maximize its chances of attracting prey in the empty dark without spending precious energy swimming around, the gulper eel turns to the deep sea's universal currency, light. At the extreme tip of its long, whip-like tail rests a complex bioluminescent organ. The eel can position its tail forward, hovering the glowing tip directly in front of its massive open jaw. In the sunless void, small inquisitive creatures spot this solitary, flickering light and move closer to investigate what appears to be an easy meal. As the curious prey approaches the glowing tail tip, it swims straight into the invisible perimeter of the eel's unbuttoned jaw. With a sudden forward thrust, the pelican-like pouch snaps shut around the victim, proving that in the bathypelagic realm, curiosity is almost always fatal. Yet, as difficult as it is to find food on a starvation budget, the deep sea poses an even more daunting demographic hurdle: finding a mate. In the bathypelagic wilderness, population densities are so diluted that two individuals of the same species might pass within a mile of each other only once in their entire lives. If a predator must conserve every calorie just to stay alive, spending energy swimming aimlessly through millions of cubic miles of pitch-black water searching for a partner is a recipe for reproductive failure. If two animals happen to meet, mate, and part ways, the likelihood of either ever finding another partner again before dying of old age is practically zero. To overcome this catastrophic spatial isolation, the humpback anglerfish evolved one of the most extreme, bizarre, and efficient reproductive strategies in the history of life on Earth: obligate sexual parasitism. In this species, the sexes follow drastically different developmental paths. The female anglerfish is the dominant hunter we often envision: a large, rotund creature equipped with a glowing lure, sharp teeth, and an expanding stomach. The male, however, is born as a microscopic dwarf, rarely growing larger than a human fingernail, and completely lacking the glowing lure, large jaws, or functional digestive system needed to feed himself. From the moment a male anglerfish hatches into the icy dark, he is living on borrowed time. Deprived of the ability to hunt, his tiny body contains only enough stored yolk energy to survive for a few short weeks. His entire existence is a high-stakes countdown against biological starvation. But while he lacks the tools for hunting, he is gifted with two extraordinary sensory systems fine-tuned for a single mission: finding a female. His eyes are disproportionately large and highly sensitive, designed to catch the faintest, unique flickering signature of a female's glowing lure across the dark void. Even more crucially, his nostrils are enormous, housing hyper-developed olfactory organs capable of detecting microscopic chemical pheromones released by the female into the sweeping ocean currents. The dwarf male swims frantically through the dark, tracing the invisible chemical scent trail left by a female. He ignores everything else in the ocean, driven by pure evolutionary instinct. If his energy reserves deplete before he locates a female, he dies alone in the cold black water. But if he successfully tracks the chemical plume to its source, he finds a giant female floating silently in the abyss. Without hesitation or courtship, the tiny male swims up to her belly, opens his specialized jaws, and bites firmly into her soft, dark skin. What follows is an anatomical union unique in the natural world. Once the male clamps his jaws onto the female, his mouth releases specialized digestive enzymes that dissolve the outer layers of his own lips and the corresponding tissue on the female's body. As the cellular walls melt away, a deep physiological integration begins. The skin tissue of the male and female knits together, seamlessly fusing into a single continuous boundary. Soon after, their circulatory systems physically merge. The fine blood vessels of the female grow directly into the body of the male, linking their heartbeats and blood flow forever. Through this shared bloodstream, the female begins to nourish the attached male. Her blood supplies him with oxygen, glucose, lipids, and essential nutrients, taking over his survival completely. Unburdened by the need to feed or breathe independently, the male's body undergoes complete retrogressive metamorphosis. His eyes wither and go blind, his fins atrophy, his teeth dissolve, and his internal organs degenerate until they vanish. He ceases to function as an independent organism. Instead, he becomes a permanent, blood-fed appendage on the female's flank, a living, streamlined, onboard sperm factory. This parasitic bond solves the demographic crisis of the deep sea with absolute perfection. The female no longer has to spend precious calories hunting for a partner every spawning season, nor does she risk remaining unfertilized in the vast, empty wilderness. Attached to her side is a guaranteed, ever-present supply of genetic material. When her internal hormones signal that conditions are right to release her egg rafts into the sea, she transmits a chemical message through her bloodstream directly into the fused male. Receiving the signal, the living appendage releases his sperm simultaneously into the water, ensuring flawless fertilization in the middle of a sunless desert. A single female can play host to several parasitic males attached to her underbelly, turning her body into a mobile, multi-partner reproductive platform. In the grand theater of the bathypelagic realm, starvation is the supreme law, and survival demands radical surrender. To live where the sun never shines and food rarely falls, creatures cannot afford the structural or behavioral norms of the surface world. Whether it is the gulper eel transforming its entire anatomy into an expanding net to scoop up rare windfalls, or the male anglerfish surrendering his very independence to fuse his life with a female, life in the deep abyss proves that nature will bend every anatomical, physiological, and social boundary to keep the spark of existence burning in the eternal dark. In the vast, silent depths of the ocean, where sunlight vanishes and the crushing weight of the water column dominates all life, traditional concepts of individual organism, communication, and acoustic propagation are completely redefined. Here, life does not always exist as a single discrete creature, and sound travels through invisible oceanic highways. To understand this deep-sea realm, one must examine four of the most captivating phenomena of the deep: the colossal colonial superorganisms known as siphonophores, the deep-sea acoustic highway called the Sofar Channel, the legendary underwater sound known as the bloop, and the lonely acoustic saga of the 52 Hz whale. Down in the bathypelagic and mesopelagic zones, where energy conservation is paramount, evolution has bypassed the typical boundaries of individual animal design. Enter the siphonophores, marine invertebrates belonging to the phylum Cnidaria, while a siphonophore, like Preya dubia or Apolemia, may look like a single, extraordinarily long jellyfish or a fragile underwater ribbon, it is not a single animal. It is a colonial superorganism composed of thousands of individual, genetically identical units called zooids. Every siphonophore begins its life as a single fertilized egg. As it develops, it does not simply grow into a single complex body with specialized internal organs. Instead, it undergoes a unique process of budding, cloning itself thousands of times over. However, rather than separating into independent organisms, these cloned zooids remain physically attached to one another, sharing a continuous central digestive canal and circulatory system. Through a remarkable process called polymorphism, these genetically identical units differentiate to perform highly specialized, singular functions for the survival of the entire colony. At the leading edge of a drifting siphonophore column sits the nectaphore region, or the pneumatophore, which acts as a float and propulsion engine. The zooids in this region, called nectaphores, are muscular, bell-shaped structures designed solely to contract and jet water, steering the massive living chain through the ocean currents. Beneath the propulsion section stretches the cyphosome, a repeating sequence of specialized functional units. Here, gastrozooids act as the collective stomachs of the colony, equipped with mouth openings to ingest and digest prey, distributing nutrients along the shared central stem. Dactylozooids serve as the colony's defensive arms and hunting tentacles, studded with densely packed nematocysts, stinging cells that shoot microscopic venomous harpoons to paralyze fish and crustaceans. Finally, gonozoids are dedicated entirely to reproduction, manufacturing eggs and sperm to propagate the species. None of these individual zooids can survive on its own. A gastrozooid cannot propel itself or reproduce. A nectaphore cannot feed itself. A gonozoid has no tentacles to capture prey. They are completely dependent on the collective superorganism for survival. Among these creatures, species like Apolemia can reach lengths exceeding 40 to 50 meters, longer than a blue whale, making siphonophores some of the longest living structures on planet Earth, drifting through the sunless midwaters like pale, bioluminescent cobwebs waiting to ensnare anything that brushes against their stinging lines. While siphonophores weave living nets through the deep water, the physical environment of the ocean itself provides an extraordinary infrastructure for long-distance communication, the Sofar Channel, short for Sound Fixing and Ranging Channel. To understand how the Sofar Channel functions, one must look at how sound waves interact with water temperature and hydrostatic pressure. The speed of sound in seawater is not constant. It fluctuates primarily based on two factors: temperature and pressure. Near the surface of the ocean, where sunlight warms the upper layers, water temperature is high, which speeds up sound propagation. As you descend deeper into the water column, temperature drops rapidly through the thermocline, causing the speed of sound to decrease. However, as you plunge deeper past the thermocline toward the bathypelagic zone, the water temperature stabilizes near freezing, remaining virtually constant. At this point, the second factor takes over: hydrostatic pressure. As pressure increases relentlessly with depth, it forces water molecules closer together, causing the speed of sound to begin increasing again. This physical dynamic creates a unique axis in the water column, typically located at a depth between 600 and 1,200 meters, depending on latitude, where the speed of sound reaches its absolute minimum. This depth layer is the axis of the SOFAR channel. When a sound wave is produced within this low-speed layer, it behaves in a physically remarkable way. Sound waves tend to bend or refract toward regions where sound travels slower. As a sound wave traveling inside the SOFAR channel starts to angle upward toward the warmer surface water, the higher sound speed above refracts the wave back downward toward the low-speed axis. Conversely, as the sound wave travels downward toward the high-pressure deep water, the higher sound speed below refracts the wave back upward toward the axis. Trapped between these upper and lower refractive boundaries, the acoustic energy becomes locked in a two-dimensional waveguide. Rather than spreading out in 3 dimensions and losing energy exponentially over distance, like a sound wave in open air, the sound energy inside the SOFAR channel travels horizontally with minimal dissipation. Low-frequency acoustic signals generated inside this channel, such as the vocalizations of baleen whales, underwater volcanic explosions, or specialized oceanographic signals, can travel thousands of miles across entire ocean basins, crossing from Antarctica to the equator without losing their structural clarity. The acoustic conductivity of the SOFAR channel was dramatically highlighted in June 1997 when hydrophones deployed by the United States National Oceanic and Atmospheric Administration across the equatorial Pacific Ocean recorded one of the most famous, mysterious underwater sounds in oceanographic history, the bloop. Recorded by autonomous hydrophone arrays thousands of miles apart, the bloop was an ultra-low frequency, extremely powerful acoustic signal that rose rapidly in frequency over a duration of roughly 1 minute. What made the bloop instantly famous, and a staple of deep-sea lore, was its sheer, unprecedented volume. The acoustic signature was detected on sensors spaced over 5,000 kilometers apart across the Pacific Basin. Initial popular speculation suggested that such an enormous sound, bearing an organic, rising frequency curve, might be the call of some undiscovered biological leviathan dwelling in the unmapped abyssal trenches, a creature vastly larger than any known animal on Earth. However, detailed scientific analysis by hydrobiologists and geophysicists quickly demystified the sound. When oceanographers compared the acoustic profile of the bloop with recordings of tectonic and cryoseismic activity, the spectral match was undeniable. The bloop was not the call of a sea monster, it was an icequake, a massive cryoseismic event generated by the cracking, fracturing, and shearing of giant icebergs as they carved off the Antarctic ice sheet or scraped against the ocean floor. The violent fracturing of thousands of tons of Antarctic ice released immense mechanical energy directly into the Southern Ocean. Trapped inside the hyperconductive layer of the SOFAR channel, those massive, low-frequency sound waves propagated across thousands of miles of deep water, echoing through the Pacific Basin until they were picked up by hydrophone arrays thousands of miles away. While the bloop proved to be a physical product of cracking polar ice, another deep-sea acoustic mystery turned out to be genuinely biological, carrying a poignant biological narrative. the story of the 52 Hz whale. First detected by Navy hydrophone arrays in 1989 and tracked systematically by oceanographer William Watkins of the Woods Hole Oceanographic Institution throughout the 1990s and early 2000s, the 52 Hz whale is an individual whale traveling through the North Pacific Ocean whose call exists at a frequency entirely unique in the marine world. Baleen whales, such as blue whales and fin whales, communicate using deep, structural low-frequency vocalizations that travel through the ocean to locate mates and coordinate over vast distances. A blue whale typically calls at a frequency between 10 and 39 Hz. A fin whale calls at a very low 20 Hz. These ultra-low frequencies are perfectly tuned to propagate through the deep water, allowing individuals to hear each other across hundreds of miles of ocean. The 52 Hz whale, however, calls at a distinct, sharp frequency of 52 Hz, much higher than any known species of baleen whale. Its call pattern is recognizable, consisting of short, repeating pulses at 52 Hz that last for several seconds at a time. Despite its unique pitch, the movement patterns of this individual closely match those of blue whales and fin whales, traveling along the North Pacific migration corridors from Alaska down to Southern California every year during the calling season. Because its vocal frequency is so far outside the standard acoustic range of other baleen whales, popular lore dubbed it the loneliest whale in the world, imagining an individual calling out into the vast blue void year after year, completely unheard and unanswered by its kind. Scientifically, the exact origins of the 52 Hz whale remain a fascinating subject of study. Biologists hypothesize that the animal may be a unique hybrid, perhaps a cross between a blue whale and a fin whale, possessing an atypical vocal apparatus that produces a higher-pitched sound. Alternatively, it may be an individual born with a rare physical deformity, or one that developed a unique regional dialect. Remarkably, hydrophone tracking over several decades shows that as the whale aged, its vocal frequency dropped slightly, moving from 52 Hz down to around 47 Hz, reflecting the natural deepening of vocal structures that occurs as a marine mammal matures. Yet, despite its unusual pitch, the whale has survived for decades, traversing thousands of miles of Pacific Ocean, proving that even an acoustic outlier can navigate and thrive in the vast marine wilderness. From living chains of cloned siphonophores drifting through the bathypelagic dark to sound waves traveling thousands of miles along the acoustic superhighway of the SOFAR Channel, down to icequakes echoing off Antarctic shelves and solitary whales calling out across Pacific basins, the deep ocean is far from a dead, silent void. It is a dynamic, interconnected acoustic and biological domain where physics and evolution merge to create mechanisms of survival, propagation, and scale that defy human terrestrial experience. Descending beyond the midwater zones and down to the very floor of the world, we reach the bathyal and abyssal benthic realms, environments defined by extreme physical pressure, absolute darkness, and vast stretches of silent sediment. Here, at depths ranging from 3,000 to over 6,000 meters, the ocean floor is not merely a barren desert of mud. It is a mosaic of bizarre geological microenvironments and surreal evolutionary adaptations. To understand how life persists on the ultimate boundary between the Earth's crust and the ocean column, we must examine three of the most remarkable phenomena on the seabed. The toxic, deadly brine lakes, known as the Jacuzzi of Despair, the mechanical and sensory genius of the tripod fish on the expansive abyssal plains, and the soft tissue biomechanics of the misunderstood blobfish. Deep beneath the waves in the Gulf of Mexico, sitting roughly 1,000 meters down on the seafloor, lies a sight that defies ordinary terrestrial intuition, a lake at the bottom of the ocean. Known colloquially to oceanographers and deep-sea researchers as the Jacuzzi of Despair, This underwater feature is a hypersaline brine pool, a body of water so dense, toxic, and distinct that it maintains its own shorelines, waves, and surface boundaries completely separate from the overlying seawater. The formation of these deep-sea brine lakes dates back tens of millions of years to the Jurassic period, when a shallow sea covering the region evaporated, leaving behind massive, thick layers of salt deposits. Over eons, as sediment buried these salt sheets and tectonic forces fractured the ocean floor, seawater seeped down through cracks into the deep salt strata. The water dissolved the ancient salts, forming an ultra-concentrated brine solution. Because water laden with dissolved sodium chloride and heavy minerals is significantly denser than normal seawater, this heavy liquid bubbled back up through seafloor fractures and settled into natural depressions on the ocean floor, pooling into vast, motionless underwater lakes. The Jacuzzi of Despair itself is a circular pool measuring roughly 30 feet in diameter and 12 feet deep, sitting like a glowing, murky cauldron on the ocean bed. Its water is approximately 4 times saltier than the surrounding ocean and is saturated with high concentrations of toxic chemicals, primarily methane gas and hydrogen sulfide, which seep continuously from the Earth's subcrustal reservoir. Furthermore, the pool earns its thermal moniker due to its temperature. While the surrounding deep-sea water hovers at a chilly 2 degrees Celsius, the chemical activity and geothermal warming inside the brine pool heat its toxic waters to nearly 19 degrees Celsius. To an unsuspecting deep-sea creature, this warm water might initially seem like an inviting refuge from the freezing abyss. However, entering the Jacuzzi of Despair is almost instantly fatal. Because of the massive density differential between normal seawater and the heavy brine, the surface of the pool acts as a sharp physical barrier. An animal that swims or crawls over the edge enters a warm, hypersaline, completely anoxic environment lacking any dissolved oxygen. The extreme salinity creates a violent osmotic shock, drawing fluid rapidly out of biological cells, while the toxic concentrations of hydrogen sulfide instantly disrupt cellular respiration. Crabs, isopods, squids, and small fishes that accidentally drift into the pool are incapacitated within seconds, dying of toxic shock and asphyxiation before sinking to the bottom of the brine. Because the hypersaline, anoxic conditions prevent ordinary bacterial decay, the bodies of these victims do not decompose. Instead, they are pickled and preserved indefinitely, littering the muddy shoreline and the bottom of the pool in an eerie, silent graveyard of intact animal husks. Yet, even in this chemical dead zone, life finds an evolutionary foothold along the lake's edges. Encircling the rim of the Jacuzzi of Despair are dense, thriving beds of deep-sea mussels. Bathymodiolus childressi. These mussels cannot survive inside the brine itself, but they line the shoreline to tap into the plume of methane gas wafting off the pool's surface. Inside the gill tissues of these mussels live specialized methanotrophic bacterial endosymbionts. The bacteria absorb methane leaking from the brine pool, using the chemical energy stored within the hydrocarbon bonds to synthesize organic matter and feed their mussel hosts. These mussel beds, in turn, create a living reef structure along the toxic rim, harboring specialized deep-sea shrimp and tube worms that have adapted to tolerate low levels of hydrogen sulfide. The Jacuzzi of Despair stands as a stark biological paradox, a lethal trap for wandering fauna that simultaneously fuels a dense, chemosynthetic oasis along its banks. Moving away from localized geological anomalies like brine pools, the vast majority of the ocean floor consists of the abyssal plains, endless, flat stretches of fine, silty sediment covering over 50% of the Earth's surface. Situated between 3,000 and 6,000 meters deep, The abyssal plains are shrouded in total, perpetual darkness and subjected to immense hydrostatic pressures exceeding 600 atmospheres. The primary physical challenge for any heavy, muscular animal living on the abyssal plain is the nature of the substrate. The seafloor here is not solid rock or firm sand. It is a soft, gelatinous ooze formed over millions of years by the slow accumulation of marine snow, microscopic planktonic shells, and fine clay particles. Any organism attempting to walk or sit on this fine sediment risks sinking into the silt, kicking up dense clouds of mud that obscure vision and clog delicate gill membranes. To conquer this soft mud environment, the tripod fish, Bathypiptera grallator, evolved one of the most astonishing structural and behavioral adaptations in the marine world. It literally walks, stands, and hunts on stilted legs. The tripod fish is a small, slender species, rarely exceeding 30 centimeters in body length. However, its pectoral and caudal fins feature extraordinary, elongated fin rays that can extend over a meter in length, more than 3 times the total length of its body. These stylized fin rays are composed of modified, rigid, cartilage-like struts that the fish can stiffen by pumping fluid into specialized vascular chambers along the fin bases. When the tripod fish descends to the seafloor, it extends its 2 long pelvic fin rays downward and its lower caudal fin ray backward, forming a rigid, 3-pointed tripod structure. The fish settles onto these 3 extended struts, elevating its main body high above the murky, gelatinous mud. By remaining perched on stilts, the tripod fish avoids sinking into the soft sediment, keeping its gills clear of silt and positioning itself in the water column precisely where slow-moving benthic boundary currents flow. Life on the abyssal plains requires maximum energetic efficiency, and the hunting strategy of the tripod fish is a masterclass in passive, zero-calorie predation. Once perched on its fin stilts, the fish turns its body to face directly into the prevailing underwater current. Because eyes are functionally useless in the absolute darkness of the abyssal plain, the eyes of the tripod fish are tiny, regressed, and practically blind. Instead, the fish relies entirely on mechanical touch and hydrodynamic pressure sensing. The long, delicate rays of its upper pectoral fins extend upward and forward like giant feathered antennas, fanning out into the incoming current. These pectoral rays are packed with highly sensitive mechanoreceptors capable of detecting the faintest vibrations, pressure ripples, or water displacements caused by tiny organisms drifting toward it. As the abyssal current flows over the perched fish, it carries small benthic crustaceans, such as copepods, amphipods, and mysid shrimp. When a drifting crustacean touches the extended pectoral rays, the mechanoreceptors fire instantly. Without using its eyes or spending energy swimming, the tripod fish feels the exact location and trajectory of the prey item. It simply snaps its mouth open, flexing its pectoral fins forward to sweep the prey directly into its gaping jaw. Furthermore, the tripod fish solves the challenge of finding a mate in the sparsely populated abyssal plains by incorporating simultaneous hermaphroditism. Every individual tripod fish possesses both functional male and female reproductive organs. If 2 tripod fish happen to encounter each other on the vast sediment plains, either can play the role of male or female, guaranteeing successful reproduction. If an individual spends its entire lifetime without ever encountering another member of its species, it retains the ability to self-fertilize its own eggs, ensuring that its genetic line continues even in absolute isolation. No discussion of the seafloor's unique inhabitants is complete without addressing perhaps the most famously misunderstood creature in the deep sea, the blobfish. Cycrolutes marcedus. In popular culture, the blobfish is often depicted as a gelatinous, misshapen, pink mass with a human-like nose and a droopy, miserable expression, a caricature that earned it the internet title of the world's ugliest animal. However, this iconic, unsightly appearance is entirely an artifact of human intervention and catastrophic decompression. In its natural habitat, thousands of feet beneath the surface, the blobfish is a perfectly formed, highly adapted deep-sea predator. The blobfish inhabits the continental slopes off the coasts of Australia, Tasmania, and New Zealand, dwelling at depths between 600 and 1,200 meters. At these depths, the water pressure is 80 to 120 times greater than at sea level, a crushing force that would instantly collapse human lungs and rupture ordinary biological structures. To thrive in this high-pressure domain without burning massive amounts of metabolic energy, the blobfish underwent radical anatomical streamlining. Shallow water fish rely heavily on a gas-filled organ called a swim bladder to maintain neutral buoyancy in the water column. By pumping gas into or out of this internal balloon, a surface fish can adjust its position without sinking or floating. However, at the extreme depths inhabited by the blobfish, maintaining a gas-filled swim bladder is physically impossible. The immense hydrostatic pressure would compress gas to a fraction of its surface volume, requiring complex, highly energy-intensive chemical pumps to keep the bladder inflated. If a fish with a swim bladder were brought rapidly to the surface, the sudden drop in ambient pressure would cause the gas inside the bladder to expand violently, rupturing internal organs and killing the animal. The blobfish completely discarded the swim bladder. Instead, evolution engineered its body out of a specialized, gelatinous tissue mass with a physical density slightly less than that of liquid water. Its flesh is composed largely of water-dense structural proteins and soft lipid matrices held together by delicate connective tissue with minimal heavy muscle or dense bone. Because its body density matches the surrounding ocean, the blobfish achieves passive neutral buoyancy effortlessly. It does not need to swim or spend precious calories to hover above the seafloor. It simply floats weightlessly, perfectly supported by the immense ambient pressure of the deep water. Under 600 meters of water, this structural design works flawlessly. The surrounding hydrostatic pressure presses evenly on all sides of the fish's body, holding its soft, gelatinous tissues in a tight, streamlined shape, resemble a typical, smooth-headed marine fish. However, when a blobfish is caught in a deep-sea research net or commercial bottom trawl and hauled rapidly to the surface, it undergoes severe decompression trauma. As the ambient pressure drops from 100 atmospheres down to a single atmosphere at the surface, the structural equilibrium that holds the fish together collapses. Its delicate connective tissues tear, its watery cells expand, and its soft flesh sags and collapses under normal atmospheric gravity. The creature that arrives on the deck of a boat is a mangled, decompressed corpse, stripped of the structural support provided by the deep ocean's weight. On the abyssal slopes, the living blobfish leads a low-energy, highly effective life as an ambush scavenger and predator. Floating inches above the seafloor, it uses very little energy to move, using broad, soft fins to make gentle positional adjustments. It drifts slowly along the continental slope, opening its mouth to scoop up edible organic debris, deep-sea crabs, sea urchins, and mollusks that cross its path. From the toxic, preserved shores of the jacuzzi of despair to the mechanical precision of the tripod fish standing tall on the mud, down to the pressure-supported biomechanics of the blobfish, the ocean floor proves that the extreme limits of geology and physics do not mark the end of biology. Instead, they mark the beginning of life's most ingenious engineering. Descending beyond the 6,000-meter mark, we leave the expansive abyssal plains and plunge into the deepest, most mysterious domain on planet Earth, the Hadal Zone. Named after Hades, the ancient Greek god of the underworld, this realm consists of steep oceanic trenches, V-shaped troughs, and abyssal chasms formed where tectonic plates collide and plunge beneath one another into the Earth's mantle. Down here, hydrostatic pressure reaches crushing levels exceeding 1,000 times atmospheric pressure at sea level. Yet, even in these sunless, high-pressure trenches, life continues to redefine the boundaries of biological capability. To complete our journey through the deep ocean, we must examine the spectral geometry of the bigfin squid, the biochemical limits of complex life in the Hadal zone, the giant single-celled architects known as xenophyrophores, the astounding discovery of dark oxygen on the seafloor, and our own footprint on this fragile, dark frontier. Hovering at the threshold where the bathypelagic zone drops into the abyssal void sits one of the most hauntingly alien creatures ever captured on oceanographic camera, the bigfin squid, belonging to the genus Magna. First filmed in the late 1980s and only rarely encountered by deep-sea submersibles since. Magna looks less like a typical cephalopod and more like a delicate, spectral marionette floating in the dark. The body of a bigfin squid is relatively small, featuring broad, heart-shaped terminal fins that flutter gently to keep the creature suspended in the water column. But extending from its small mantle are 10 extraordinary appendages, arms and tentacles, that reach lengths up to 8 or 9 meters, making the appendages more than 20 times longer than the squid's main body. What makes Magna truly unique is the bizarre right-angle geometry of these limbs. As the squid hovers in the water, its long arms extend straight out horizontally from its body before making a sharp, perpendicular 90-degree turn, dangling straight down into the deep water like long, delicate fishing lines. Scientists hypothesize that the bigfin squid uses these sprawling, thread-like appendages as a passive web, drifting silently through the bathypelagic current while the lower sections of its tentacles trail along or just above the soft ocean sediment. Microscopic, sticky suckers along the appendages ensnare small benthic or pelagic organisms that drift into the living trap. When a prey item touches a line, the squid retracts the affected appendage, bringing the meal up to its central beak without expending valuable energy chasing prey through the dark. Dropping further down into the Hadal trenches, past 7,000 meters, we enter a world where the physical chemistry of life encounters a rigid, non-negotiable wall, the biochemical pressure limit. For decades, marine biologists wondered why no fish species had ever been observed in the deepest parts of ocean trenches, such as the Mariana Trench at 11,000 meters. The answer lies not in a lack of food or oxygen, but in the structural integrity of biological proteins. At extreme hydrostatic pressures, water molecules are squeezed so tightly together that they disrupt the delicate hydrogen bonds holding proteins, enzymes, and cellular membranes in their proper three-dimensional shapes. Under hundreds of atmospheres of pressure, ordinary cellular enzymes flatten, lose their functional structure, and fail to catalyze vital life processes. To survive in this environment, trench-dwelling organisms rely on an extraordinary organic molecule called trimethylamine N-oxide, or TMO. TMO acts as a molecular chaperone, binding tightly to water molecules and stabilizing the complex folding patterns of cellular proteins, protecting them from collapsing under ambient pressure. As marine animals live at progressively deeper depths, the concentration of TMO in their muscular and cellular tissues increases linearly to counteract the rising pressure. The absolute champions of this deep-sea biochemical feat are the Hadal snailfishes, such as Pseudoliparis soirei. The Mariana snailfish, living at depths between 6,000 and 8,200 meters, these pale, scaleless, translucent fish thrive in an environment that would instantly crush most organisms. Their bodies are packed with exceptionally high concentrations of TMAO, allowing their internal enzymes to function smoothly under immense pressure. However, biochemistry imposes an absolute ceiling. Math and physiological models show that to survive past approximately 8,200 meters, a fish would need a concentration of TMAO so high that its internal cellular fluid would become more concentrated than the surrounding seawater, causing lethal osmotic fluid imbalance. Thus, 8,200 meters represents the universal biochemical limit for vertebrate life on Earth. No fish can exist below this threshold, leaving the deepest bottoms of the trenches to invertebrates that utilize alternative structural biochemistry. At the very bottom of these deepest plains and trench floors, where vertebrate life cannot tread, the seafloor is ruled by creatures that challenge our fundamental understanding of cell biology, the xenophyrophores. Belonging to the class of single-celled protists known as foraminifera, xenophyrophores are not complex, multi-celled animals. A single xenophyrophore, such as Syringamina fragilissima, is a giant single cell containing thousands of individual nuclei floating within a unified mass of cytoplasm, called a syncytium. While most single-celled organisms on Earth are microscopic, xenophyrophores can grow to over 20 centimeters in diameter, making them some of the largest single-celled structures ever discovered. To construct these massive, fragile homes on the mud, xenophyrophores act as master architects of the sediment. They absorb microscopic particles of sediment, sponge spicules, radioactive heavy metals, and tiny mineral grains from the surrounding water, gluing them together with an organic cement secretion to build delicate, complex, shell-like structures called tests. These tests form elaborate labyrinths of chambers and frills across the ocean floor. Despite being single cells, xenophyrophores play a critical role as ecosystem engineers on the abyssal and hadal plains. Their complex, raised test structures provide physical shelter, nursery habitat, and hard attachment surfaces for tiny nematodes, crustaceans, and marine worms on an otherwise flat, featureless plain of silt. Furthermore, by concentrating heavy minerals and organic matter within their bodies, xenophyrophores filter and process the abyssal mud, acting as vital biological recyclers at the absolute bottom of the world. For centuries, scientific consensus held that all oxygen on planet Earth was generated by photosynthetic organisms, plants, algae, and cyanobacteria, using energy from sunlight to split water molecules. Because sunlight vanishes completely below 200 meters, it was assumed that the deep ocean was strictly a consumer of oxygen, relying entirely on downwelling ocean currents to import oxygen-rich surface water. In recent years, however, a groundbreaking oceanographic discovery shattered this long-held paradigm, the discovery of dark oxygen on the abyssal seafloor. While conducting deep-sea research in the Clarion-Clipperton Zone, a vast abyssal plain in the Pacific Ocean situated 4,000 meters down, scientists measuring oxygen consumption on the seafloor noticed something impossible. Instead of oxygen levels steadily dropping inside sealed benthic research chambers placed on the mud, oxygen levels were significantly rising. Oxygen was being actively produced in complete, total darkness. Subsequent investigation pinpointed the source of this dark oxygen: polymetallic nodules. These potato-sized mineral deposits, which sit scattered by the millions across the abyssal sediment, are formed over millions of years by the precipitation of metals out of seawater, containing high concentrations of nickel, copper, cobalt, and manganese. Researchers discovered that these polymetallic nodules act as natural geobatteries. Different metal layers within a single nodule create a chemical potential difference, generating small electric voltages across the nodule's surface. When multiple nodules sit close together on the seafloor, their combined electrical charges can reach up to 0.95 volts, close to the voltage required, 1.23 volts, to drive seawater electrolysis. This natural electrical current splits surrounding water molecules into hydrogen and molecular oxygen without requiring a single photon of light. This discovery proves that the deep ocean possesses its own abiotic, light-independent source of oxygen, reshaping our understanding of how life might have originated on early Earth and how it could exist on dark, icy moons across the solar system. Yet, just as we begin to uncover the deep ocean's ultimate secrets, this remote, fragile wilderness faces unprecedented threats from human activity. For over a century, humanity operated under the illusion that the ocean's vast depth and volume offered an infinite buffer against human impact. Today, research reveals that even the deepest trenches on Earth are no longer untouched by the surface world. Deep-sea landers exploring the Mariana Trench at 11,000 meters have documented high concentrations of microplastics and synthetic fibers inside the digestive tracts of hadal amphipods. Persistent organic pollutants, such as PCBs, which were banned decades ago, have accumulated in the fatty tissues of trench-dwelling crustaceans at concentrations higher than those found in animals living in heavily polluted coastal estuaries, carried downward by the continuous, toxic fallout of marine snow. Even more concerning is the looming prospect of commercial deep-sea mining. The very same polymetallic nodules that generate dark oxygen and provide critical habitat for abyssal life are rich in rare earth metals desperately sought for surface technology and battery production. Stripping these nodules from the abyssal plains would destroy ecosystems that required millions of years to form, kicking up massive, toxic sediment plumes that could drift for thousands of miles through the water column, suffocating delicate filter feeders and disrupting midwater food webs. Our journey through the deep ocean, from the sunlit upper bathyal slopes down to the silent, crushing depths of the Hadal trenches, reveals a domain of radical beauty, infinite patience, and staggering evolutionary genius. In a world of perpetual darkness, high pressure, and scarce food, life does not merely cling to existence. It reimagines what it means to be alive. From the red night vision searchlights of the stoplight loosejaw to the parasitic union of the anglerfish, the sprawling nets of cloned siphonophores, the standing stilts of the tripod fish, and the natural electrical batteries of the abyssal plain, the deep sea demonstrates the absolute boundless creativity of nature. As we stand on the shore of this vast, dark frontier, looking out over an ocean that remains over 80% unmapped and unexplored, we are reminded that the deep sea is not a hostile void separate from our world. It is the heart of our planet's living biosphere, a silent, glowing sanctuary that demands our wonder, our humility, and, above all, our protection.